Good afternoon, Firoza. Could you hear me?
Yeah, good afternoon, sir. Yes, sir, we can hear you, sir.
Yeah. So we start the session, and we start the session here. And to all the participants, there is Roja will be sending one link in the. Roja, can you please put up a link in the this YouTube streaming in the chat box or somewhere so that all the participants can access it. And this particular session from now onwards will be are going to get streamed on our YouTube channel. Okay, so everybody can just share the link with all the interested people in their group, and I request the people to share the link to the different groups so that the wide for number of you can say students and faculty members in the country, or I say around the globe, can get benefit out of this. So we share the link in the chat box, and that can actually be shared with whomsoever you want. And with this, I really warm welcome Mr. Harish and Swami, and pass the baton to Ms. Roja, who will now coordinate all the activities for the day. Yeah, Roja, anything?
Yeah, thank you, sir. A small announcement, sir. For all the registered participant, I would request you to please join by the YouTube meeting link that will be shared with you, the event link, because an attendance will be generated, and based on this only, we will be monitoring you all. So I would request the registered participant to please join by the meeting event link, which will be forwarded to you every day in your mail. Thank you, Gaurav, sir.
Yeah, and so I have to attend something at a very personal level that actually I share with the other participants with a very heavy heart. Professor Ratnesh Bhattacharjee, who is my colleague and who is you can say the principal investigator of this particular program with me, he has lost his father at the same time he started this course. Unfortunately, that's why I'm taking leave for the day, as I have to visit his home and maybe the cremation ground. So his father was really a genius, I mean to say, because he invested his entire life uh, for the social cause. He was a teacher and he started the first school in the Silchar region, which is precisely in, you can say, the deep down southern Assam. And he did really a lot in the for that particular locality and the Assamese community in general. And he was, I think, he has crossed 90 years of the age, on 80 or 80, I think 80 years of the age, and was suffering from one life-threatening disease. So I'm going to say he met his creator and went to the heavenly abode. So I wish peace. I wish that his soul will reach in peace. And with this heavy heart, I pass this information uh, and uh, and this path we can see the coordination of the course for the rest of the day to Miss Pooja as well. Thanks a lot, and thanks everybody who is here. And I will be available. I will be coming back shortly after completing a few, you can say, attending few rituals, and I will be joining you back shortly because this program will be here today by 5. Thank you, and thanks a lot for all the participants, and wish all of you a very, very good luck for this particular because the course we have registered. All the coordinators, they have really made this you can say difficult task a reality one. And thanks once again, Intel and Mentor Graphics for your support. Thank you. And
Thank you, sir.
last but not the least, I really thank Mr. Puneet Goyer, who designed this particular course with Intel and Mentor, and and I think the entire community will get benefited out of this. Thanks a lot, Puneet ji, and see you soon. Thank you. Bye bye.
Thank you, sir. I would request Mr. Harish Narayan Swami, sir, to please start with the session, sir.
Suroja,
Harish, sir? Yes, sir.
Can you, now this onward, I request you to please introduce Harish sir to the participants, and then you please start the session. Thank you.
Okay, sure. Thank you, sir. So we have with us Mr. Harish Narayan Swami, sir. Harish Narayan Swami, sir, is an application consultant for the emulation at Mentor Graphics, and he is having more than 15 years of experience in the EDA tool designing. He is working with Mentor Graphics for the past 15 years and has done a lot of projects and has worked in the IC design area. So with this short profile, I would invite Harish sir to please start the session. We will be really happy to hear you, sir.
Thank you, Firoza. Thank you. And, also, thanks everybody and GT sir also for this opportunity. But as he said, he is moving on for an important job, and I would share my sad condolences to him and to his friends. With that, I would like to start with the session. And I think one thing from morning, what I'm seeing is really a good topics of discussions that I'm seeing is because I know as you started, you saw that industry is trying to run fast, and there's a lot of more complexities is been increasing, and they need a solution. So while we talk more on these type of solutions, especially into the digital world, and the digital world has a part of it has the IC, the integrated circuits. So I think it is a very good sessions that I am seeing, and it should be helpful for all the academics, because this was what was missing during our days, and we see that this is growing now, and academics is giving importance on the such type of topics, and helps grow the industry much faster, and also that way it gives us a more solutions wherein you come out with a lot of digital applications, or the applications that helps us run our life daily life more smoother. So I will just start with the emulation. I know people were talking about how do you verify and um, the complex things that's going on in the digital world. How are we going to design that? And what's the solution on the helping the designers to resolve all that they have designed has been working as it is expected. So when I say design, it can be of any type of applications. So we talk more on the digital world. So when I say in the digital world, his comes into the integrated circuits. So integrated circuits has both digital and analog, but we would be concentrating more on the digital part. And during with this digital world, like how we are going to actually get the silicon out, and when we have to get a silicon, there is a flow, like where the designer starts understanding the specs and designs his specs by writing an code, and this code can be of any language. It can be C++ or HDL language. So when you have written this design, or written this code, how do you verify the given written design so that it works fine? But now the design is small, it's fine, but it's growing and growing, and you heard that there's a big lot of complexities. So what we would be looking in today's session is, I will just give you a glimpse of the solutions that is available as a part of verification. And I will start with some quick idea of like what simulation, FPGA prototyping, and then see all those challenges, and what is emulation, and how is emulation also trying to overcome those challenges, and also help in the industry challenges in the terms of how do they build the integrated circuit. So this is what is my idea of sharing today. So I'll just go over these topics, and to start off, and I just wanted to give a glimpse of what is the industry is looking is, because that's where uh, a lot of work has been done. I know today morning Ruchir already discussed about this, saying that there's a huge investment of R&D, and especially we are seeing companies like Facebook or Amazon and Alphabet or Netflix or Google and Apple. They are investing a good lot of investment. I would say it's billions of dollars on their R&D. Is mainly is not only to bring up their own product, but they wanted to get their product being more efficient, in the sense like they started having their own silicon so that it can process huge number of huge data that's available now. And that's where the trend is going on towards AI ML, where they can use those type of algorithms and have those being computed by using an hardware by itself, which we call as an integrated circuit. So earlier, else it was just more of the programs that would collect the data and process it, but they feel that those programs may not be sufficient enough, so they started investing on semiconductors. So this is where, and we also see that, so when you start verifying or building those integrated circuits in terms of an ASIC and applied application specific integrated circuit, there's a big investment on the hardware assisted verification, in the sense like they say, since the complexity is increasing, as we always talk, and it needs a better hardware to compute a big, huge data that's available, that's coming up in the market. We have already seen in the morning discussion with Ruchir talking about, like Geo or the data centric that's coming up, that has been available, which can be easily, means should be computed fast enough and get you the results, or make your life much more easier as you start moving around with the gadgets that you carry around. So for this, we see that the industry has also started investing a huge onto these verification of these uh, ICs or ASICs. And not only that, the hardware assisted verification has itself is an hardware. So the ones that hardware that we're using was earlier was mainly for like a verification of your complex CPUs and GPUs, but now the CPUs and GPUs are being growing much more, like as becomes a data center. It was not like more of a desktop PCs or which was earlier, but now it's become as a data center. Then it becomes into servers. But now as soon as you have a servers, we started seeing good lot of other applications in terms of multimedia. And then when multimedia came into picture, the networking came into picture to connect the whole of the system, and then storage started coming in. So it started growing and growing, and you see now the mobile and automotive and IoT is coming into picture. So, but now the designs complexity started increasing as the time goes on, and now we started looking into AI ML, which is another, and automotive, which is another one which is actually driving this market. To have all this type of verification, we need to also have a certain solution that can be easily accessible, and also be worked efficiently, not only at your one place, or it can be accessed virtually from other places also. So just to make it saying that the hardware accelerated solutions is not now being like a desktop, which is just lying next to your system. It's also become like a data centric friendly, in the sense like, the emulators or the hardware that you wanted to verify is also sitting in a lab across the world, and people can, access that remotely. So which is also becoming like an virtualization of your solutions that you wanted to verify on hardware. And not only that, with the where Mentor has been also invested a little more onto it by bringing out as a Velocity Strato, which is by itself as an hardware. Since it's going to be sitting at enterprise level at one of the global place, and it can be accessed across the global. So the cost of investment on such hardware and maintenance reduces, is because it can be remotely accessed and shared across multiple groups, or across multiple applications of the same organizations. So that's where we see that emulation by itself is completely evolving across different domains, and even within the organization. So, but what's trying to drive this more and more. As I spoke to you all earlier, it was CPU, GPUs, but as the entertainment, or as the digital world started increasing in and trying to get into our daily life, we started seeing that multimedia and storage came into picture. But as we see now, there has been a huge data across. We need to have a good networking, and wherein it can collect all the datas, and it can be processed. And now processing that as it is also very complex part. So that's where in the AIML is coming into picture. And now that we have the automotive, so automotive is becoming more and more friendly, like autonomous driving, and not only like HADAs like try to do a lot of its own braking system, automatic braking system, or try to analyze what's coming in ahead, and trying to do a lot of automotive based automation, wherein the digital world is being involved into it. To drive these things is what now driving more onto your system to make your digital world much more user friendly, or much more accessible. But to get those accessible and drive in all those complexity into a chip, which can be an ASIC or an FPGA, so how are you going to now push all those complex technology into the hardware, is what we would be now talking more. And just to start off the traditional flow, the way the people, means earlier the chip development used to happen is people write a code in the block level and then stitch it as a completely as an chip level, and then it goes into the fab. So once it goes into the fab, then there was a complete system integration used to happen uh, along with the other peripherals, and then write a software on top of it. This used to take a good lot of time to get into the market, but nowadays with the as the technology improved, with the verification solutions that is becoming more and more advanced, we start trying to reduce time by having the fab ready, means have the complete SOC being validated before it goes into the fab. Has the system has been written or the code has been written, so you can start porting onto an hardware or a simulator, and also integrate with your peripherals and run the software on top of it just before it actually becomes hard as a silicon, and have the complete validation of an SOC wherein the hardware or software bugs are being isolated and fixed before it goes to the fab. So this is possible is because you have an excellent hardware accelerated solution that is being available today, so that you can reduce the time to market, and release the silicon as early as what you had earlier been doing it. So now just to get an idea, like what is this emulation, or what is the flow that comes into it and where it's been used. It's used in an ASIC and FPGA flow for designing of any of your ASIC chips, or or porting your FPGA, and use those particular FPGAs for your applications for your given designs. So the flow of designing an FPGA or an ASIC is, it starts with the functional specs, and then you write an HDL code. So HDL code can be a Verilog or VHDL, and then you try to synthesize that so that it can be converted to an hardware, is where we call as synthesize with reference to the technology that you would like to go. And then there are a lot of other flows of verification to make sure that the code, and once it goes into silicon, and there's no much fault, like so where you actually do is the for DFT, the fault testing, and then you do a place and route for a given die or for a given FPGA, and then you port your design onto it. Is one way is an FPGA, while on an ASIC you actually send the uh, place and route data to your foundry, so that it's the flow planning data to the foundry, and then the foundry does the place and route, and also in parallelly verifies the design, and then get into the silicon. So this is a very generic flow that goes between an ASIC and an FPGA. In an ASIC, it gets into your silicon, while on an FPGA, you have the FPGA chip by itself readily available, wherein your design has actually synthesized, placed on route and burnt onto the hardware, and those chips is being used as a part of your applications. So this is how the flow goes in, and we would like to see where this in this flow, wherein our verification or the hardware assisted verifications comes into the picture in a complete enterprise verification platform. So we would look a little bit more into simulation, emulation, and prototyping, which is a part of the verification flow, as I said. So once you have the code, now you need to actually validate the code that is being written, and also confirm is it as per the specs. But when you get into that, there's a huge lot of test patterns or the test that has to be done as part of your verification. So now we'll see what all the different verification solutions are there, and then we will see how what all is limitations and challenges, and how do we resolve that. So to start off, I will just just to give a quick glimpse of what is simulation, and then go into what is the next steps of FPGA and emulation. So when I say what is simulation, so simulation, it is just a model of complex system where you could be able to manipulate the model and observe the result. And the systems can be complicated, interactive, and dynamic. It can change at any time with reference to the given model. And a model is nothing but is an abstraction of the real system that you wanted to design, consisting of multiple objects. So when I say objects, it can be multiple blocks which will interact each other with a certain set of rules that would be there. So this is how a complete spec would look like. And there is a different type of simulators that is available to simulate your written code. So there are one is like HDL based, where it is depending upon an event based or cycle based, and the other one is an emulation based. The emulator based is what we would also look. That's an hardware based. That's an hardware based simulator, and the schematic based, it's more like on the fly. But this is very small, and is just more onto the learners. But as you start developing your ASIC designs or FPGA, you would start using HDL and emulator based. So just a quick glimpse of what is HDL based simulators. So there are simulators where it is based on event based and um, cycle based. Just to give an idea like what is event based, is because so we need to understand how the verification actually happens and how fast it can be computed. So when I say an event based simulation, so it is actually a software which computes all your nodes on your design, and then tries to evaluate and present it. It's like continuous computation which uses a lot of CPU farms on your host machines. For example, when I say like an event based, so event based is like it tries to extract the information at every node point, especially at the outputs, uh, only when there is a change in the event. But now, for example, if I take A and B, so when you with an NAND gate, so you see there's A is 0 and B is 0, so the output is 1. But B changes to 1, but there is no much change is happening. So it is still 1, 0 and 1 is 1 on the NAND gate, and you see there's no change. So this is not recorded, but event-based simulations will keep a track of all the information of all the nodes. So it needs a lot of memories to save all this information. As soon as the A changes to 1, so then you see the C is driving down to 0, and there's an event. So like this, the computation will keep a track of all the data, and it also understands, okay, at certain time is when is actually the event is changed. So it tracks the time as well as the value continuously. So this happens, say for example, this is for one of the logics, but now it happens for all the logics, all the registers and state element in your design. So this is how the event driven simulation runs. While there is another another mode of simulation, what we call as cycle based. So cycle based is something like instead of an event where there's a change, but cycle has depends upon a clock, that every clock edge it starts storing the data at every registers or state elements like latches or flops at every node points, other than the actual internal nodes. So it carries it in, captures all the information at every clock edge at the boundaries of your latches or state elements, and then it tries to, propagate internally and saves the data. It assumes that the whole of your clocks is in synchronous state, but it works even for asynchronous. So there is a process and method internally that works out to make sure that whether the clock is synchronous or asynchronous, but it just makes sure the whole design gets into a synchronous mode and captures. So this is how the cycle based happens, but cycle based will never look into the timing, and it just only looks at every clock edge, what was the data was existing at those boundary nodes. So this is much faster, but since it is not going to store any elements, state elements or of the data, it is just only checking at every clock edge. So this would be much faster when the design is bigger. While when you say event based is good when it is designed so smaller, but it helps you out in analyzing much more of timing, and it can find some glitches. But in the cycle based, you don't find those timing because it runs at every clock edge. Hence, a cycle based is much faster than the event driven, and also requires less memories because it's not going to store anything. It's just going to catch up at every edge what is the changes is happening. While, as I said, cycle based does not detect glitches, or doesn't worry about setup on hold, but it does make sure that there's a change in the data. While event driven based simulation does check for your timing analysis and finds the glitch. So this is the type of simulations that is available as a software based, which actually gets computed onto your hardware, means on your host machine. Sorry, it runs on your host machine for a large, integrated large designs, which could be of, from small millions to a billions of gates for your design of the design, and also run softwares onto it. Like software in the sense it can be an OS like an Android OS or any of your applications softwares on it, and then that becomes a huge number of cycles. To handle those, it needs a multiple CPU farms or multiple CPUs to process all those things as a part of the simulator, which by itself, is a challenge because it has to now process all the code that is written in hardware in HDL language, hardware descriptive language, and compile it and compute this completely on your host machine. So that itself becomes a challenge for the simulation, and it hits a barrier with reference to the size of the design and also the how long it's going to be computed or how long it's going to be running the test. So for this, what we have seen is having that run into the hardware. So that's what we call as an emulation, which is a solution, which would be the solution that would help in resolving the limitations of the simulators that can now start verifying a bigger designs. So as the designs were growing bigger, or finding a new way of running, validating as the hardware, where all hardware assisted verification is now called as emulation. So we will just go how this actually started. So since now that we have the software-based simulation, which is, we know that it is slow, and it becomes challenging when the design grows big. So we needed some type of algorithms that can be driven on the hardware itself so that it can be computed faster. So this is just for an example to just say that, a EEPROM based emulator wherein there's a lot of digital circuits and, also a few programmable chips which can be designed like an emulator, which can be, mapped your actual netlist onto the hardware and run your software on top of it. So these were the small emulators that they started doing it so that, it can run or verify a lot of your digital circuits on the hardware itself. So if you see, that's how the hardware started coming into picture, and which actually improved the performance. And this is how the start of the emulator began, as a start of prototyping. And we understand that as per our, if you see the Google or something, you would see that Pentium was actually emulated on a Xilinx 3.5. This is a very old FPGAs, probably around 2003 or something. So this is old FPGAs which was used to validate a Pentium code, based code on the hardware. So just to start of this, people had started using an FPGA because FPGAs started coming in and became more user friendly so that they can program it the way they wanted and put their code onto it and run those designs that you plan for SOC and not only verify that, you can also run your software on top of it. So this gave us a complete SOC verifications wherein you can have both hardware, the code that is written is ported onto it, and also you can run software on the same board. So this is where the prototyping came into picture, where the prototyping is to use FPGAs for making the whole system to run and or verify it much faster. So that's where not only that, it also gave an advantage is to create a demo platform for especially for the customers once they've developed their SOCs or the chips that they wanted, and they can share the whole platform itself as a complete solution. So just before they actually tape out their SOC or tape out their FPGA itself, so that the customers can actually validate whatever they have planned to design. So normally, if the design is smaller, you can always put in one FPGAs, but as you know, that complexity is increasing and the design size are bigger. But once the design size are bigger, then you need multiple FPGA components so that you can uh, partition the logics or partition a complete SOC into multiple blocks, which goes into multiple FPGAs and connect to each other and work as a single FPGA so that verification environment becomes as if it's running on a one FPGA. But the challenges is that you need to have to run the whole thing in a flow where whether it's an RTL or a gate level has to be now analyzed or compiled. And not only that, once your RTL code is compiled and it has been synthesized, now it has to actually map across the multiple FPGAs. When it has to map across multiple FPGAs, it has to do a pin muxing in such a way that this block, one of the block goes to the FPGA 1 and the second block goes to the FPGA 2, and then how it is going to be communicating between one FPGA and the other FPGA. So there is something called as pin muxing so that you can partition into multiple FPGAs. And then you do a place and route, and then you port the whole design onto multiple FPGAs and you run it. So this becomes a bit complex as the design size grows, but it is feasible. But since it becomes complex, it takes time to compile for each and every FPGAs. But again, with those coming into picture, the debuggability is a challenge, is because you have a limited. You actually have to give the probes for signals that you wanted to actually have a visibility, wherein when you run your tests, so what is the data for the nodes that you need to be collected. So those has to be as a probes or a signals that can be viewed as a part of your waveform. So that adding all those things increases the infrastructure of your the whole setup that you're going to verify. So that becomes by itself as a challenge, but it is possible. And as the FPGAs is now becoming more like an ASICs earlier. So it was a very tight schedule is to bring up the designs much faster and verify it and release it to the customer. So that was a biggest, challenging to finish the design verification much faster. So that needed faster debug and also catch bugs and try to avoid a lot of spinning iterations, is because changing or once the FPGA is burned, then new FPGA has to be picked up. So there's also a cost involved into it. So debuggability was a challenge over here. So that's where it came up as the roadblock. And I don't say it's as a roadblock, but it's a barrier where it needs a lot of time. So if you see that you have a simulation and then you have an FPGA now. So FPGA has his limitation is in terms of debuggability, but there are a lot of tools that you can even add on to it to increase the number of probes. But again, the limitation is you don't have the complete visibility over there. But the technology has been changing in terms of a lot of tools that has been coming up. But again, as the design goes big, then you'll have to have stitching multiple FPGAs. So there's some limitations over there in terms of debuggability or porting multiple FPGAs or connecting in multiple FPGAs to represent as a single FPGA, while the simulation has a limitations to run long tests, so it is good for a short test, and it provides full visibility, and it can have the advanced features like assertions all onto the simulation that will help into debuggability. So this becomes a completely both still is a roadblock in the sense like it isolates of getting not only verifying it faster and also catching off the bugs, but also it's difficult to isolate the digital from the actually analog bugs also. So this way, what we have seen is the emulation by itself as a solution in between the simulation and the FPGA, which will complement to the simulation as well as to the hardware, with the idea of porting it more easily and have a complete visibility on the hardware, and which gives you more like a simulation kind of environment, but running it onto the hardware. But now this is where a slight difference is that this is more dedicated only for verification, but this will not be used as an application like the way FPGA can be used as a prototyping, but this will help you to compile faster, or run your tests much faster, and also debug, and you can be able to isolate that the issues are in the digital or the issues are outside the digital world. So that can be easily isolated, so that once it's verified on the hardware, so all your digital environment is good. And once it has been running in the mixed, so you know that the issue that comes is only in the analog, and this way you can isolate digital and analog issues with the emulators. So what if you don't do these emulations, or do this hard verification? People have seen that they've ended up into bugs earlier, and that made people to see that emulation or hardware accelerated verification is a must for their designs. So that's where we see that those changes came into picture. And now with the age of space age, emulation looks to be a must for the complete verification as an hardware assisted verification. So just to start with, now what is emulation? So I'm just trying to use Veloci as an hardware as an example everywhere, since it's from the mentor. So I'll just start with what is an emulator. So emulator is an hardware which is actually, as I said, it's complementing both simulator and the FPGA. So it's a huge, like a supercomputer with all for modeling all your digital integrated circuits. It can also run your OS on applications on the hardware, which will actually imitate your actual design or your SOC as if it's lively available, so that it works as if it's working with the real data on top of it. So this is how the emulator gives you the realization of your SOC, and then you can verify and debug very comfortably onto the hardware, since everything is into the real world running in zeros and ones, while your simulator is running with a 6-state mode, not only 0 and 1, it works on X and Z, and there's other states. And on the emulator, it gives you a high reliability and high accuracy. It runs much faster than the simulator, but it may not be as faster, or it might be a much slower than your real-time world is, because it's going to scale down your performance on the hardware. So that's where the emulation is. And why do we need emulation again? So as I said, we were discussing a lot on the having a simulator and also having an FPGA board. So what happens is, if you see, it is easy to bring up on the simulator, uh, but while if the design size goes bigger and the performance is high on an FPGA prototyping, but bring up time is much faster, much slower. So that's where we say that it is hard on the FPGA bring up, while it is easy on the Questa. But in between, as I said, we have emulation as a solution. That is where we need emulation to as a part of your verification cycle, wherein it gives you a simulation kind of environment. Like, it can not only run faster, but it can also have the limitations that had debuggability in the prototyping can be also debugged onto the hardware. So there is always a flow. Like, people ask me, oh, I have simulator, I have FPGA prototyping, so how useful is an emulation? So emulation, as I said, it's a complementary. So you can use a simulation to stitch your design and port it onto your hardware, and run long tests that it will take normally, which takes days in the simulation, which will finish it in few minutes or seconds, depends few minutes in the hardware. And the same, once it is, if there's an issue, it can be debugged and then run onto your prototyping board much faster. So this way you can have the whole application running onto the hardware, and it goes into the actual prototyping. So this is where we say emulation is a must, so that it will reduce your time to the market. Just to give a glimpse of how the emulation also evolved, and as we saw that the designs were earlier were small and the usage was less, more towards only your CPU or GPU for your as a part of your PCs. But as it started growing, the designs became bigger, and need to for verification methodologies was high. So Mentor, this is just an introduction on the Mentor solution. So Mentor also started with the same trend, where we had an FPGA based an emulator, which used to have, like, 1 million gate in 1996, and we had a 2004 vStation Pro, which used to evaluate, means verify 60 million gate of the design. And we had a Celero. So Celero was a custom chip, so it was a chip designed only for verification, while we had an vStation, which was an FPGA based emulator. So, but there we had built up all those infrastructure, but it takes a lot of compile time. But custom base was much faster in the compile. While this was a small footprint, but it was good in the transaction base. So what we did is we pulled out all the best parts of the hardware, and we clubbed both of these into a new solution called as Veloci, and which has a custom chip. That means we developed a chip for an emulator, which will actually work as if it's like in a simulator, by taking all the good features of the hardware which was used for in the FPGA and the vStation Pro and in the Celera, where now that it can compile faster, and it gives you a best runtime and with model accuracy, and also it has a good transaction based acceleration. That means it can communicate between your test bench and DOT much faster and efficiently. Overall, it gives you like a simulation kind of environment, while the backend is running on the hardware. So this has been evolved, and there's a good lot of experience of 10 years, and now we have a Strato, which is still again improving. So I will just use this as an example, like what all emulation should be doing it, or that has been helping in the industry to resolve a lot of the ASIC or an FPGA based issues. So as I said, the way we grow is we found that the limitations were the different emulators based or a custom chip. So that what was missing is we developed all those things into our own chip, what we call as Mentor Crystal chip. So this is not a commercial chip. This is mainly used only for emulation. When you verify your code as if you are verifying a code on a simulator. So this has a complete, details, or complete methodologies, or technology that is being deployed into the same one chip, so that it can communicate with your host machine very comfortably, with a higher communication bandwidth and more optimized way of communication. And it works with both copper wire and as well as optical fiber. And since this is our own chip, so we understand how this can be compiled, and the technology has already, we know what's the technology. So whatever the RTL is there, it gets synthesized with reference to the Mentor technology. just because it is going to be ported onto the mentor hardware. And it gives you the full complete visibility, which was a limitation as a part of the debug whenever you're running it on the hardware. So what we did is we have built in a debugger internally so that it gives you a complete visibility. As you start running the design, you can actually capture the waveforms and look at every node point of the information. So not only that, as the design size grows bigger and bigger, uh, it needs to have much more FPGAs to be communicating each other and connect to each other. So this is how we have built in something called as virtual wire technology, which is again built as a part of the chip itself, so that it knows how to communicate between multiple FPGAs, and it gives you as if it's a single FPGA for a user, so that he's not much worried that okay, he has to do how to stitch your multiple FPGAs with pin muxing or you know, partitioning your design. So all these information that we manually do it is now converted into the technology solution, and it is ported into the hardware, which in turn gives you a complete emulation on a chip, what we call as a custom ASIC chip for emulation. So if you just a little bit information on the chip is that all the logical arrays is what we call as macros or MFUs, which is similar to an FPGA. We have a block RAM, similar to block RAM. We have some type of cache memories we call as XC and L memories. So this is where your actual user or design based memories get mapped. Track and FPGAs, we have a trace control. We have node informations, and there's a debug engine which can help you into start and stop or complete verification, which gives you a feel that okay, this is how the simulator works. So it gives you the control of it. So this is how the technology is being developed onto an ASIC chip. So this chip is used as a part of emulation. So we have each board wherein 16 of these ASIC chips are being ported, which completely makes as if as a single board is used only for verification, and it cannot be used for any of your application. But you can port your SOC on it and then verify or run your test as if you're running it on your simulator. So this way, as I said, it gives you 100% visibility. You don't need to recompile because you have left out that some signals are not there. So it doesn't worry about the list of signals that needs to be probed or triggered. And it communicates between each board or each chip as if it is a completely, you know, as if like a single FPGA, and it supports both asynchronous and synchronous. Asynchronous, it goes up to 16, domains of clock. So this is how the design of the emulator is done, so that you get complete advantage over the simulation and the prototyping, so that the design is completely validated before it actually goes into it. Just to take an example, I just took an example like, Mandelbrot set. Actually, I thought I'll show the demo, but as the time permits, I will just go ahead and give you a quick demo of it. So I just wanted to show you like if an equation, a complex equation, what we call as a Mandelbrot set. It's an equation where you actually try to, change the value of a C in terms of real and imaginary. Whenever it is real and the data gets computed and iterated, and it presents gives you a stable data, and once those data is actually plotted, you get a graphical view as this picture. And as the data goes unstable outside the value more than 2, it goes unstable and the picture formation is not there. So which actually gives you an idea that whatever the data is there is within that 2D data, what we call as Mandelbrot set. Uh, it's called as a Mandelbrot set, and it's a set of points whose boundaries are distance and easily recognizable by 2D fractional shape. That's where I was telling you about real and imaginary. It's a set of images, and it's made by sampling complex numbers to determine for each whether the result tends towards infinity. So when it tends to infinity, the color changes, but it is still within the area of the color code. Normally, I think, if you go more in detail, you could actually Google and get into it. But treating the real and imaginary parts of each as if is an image coordinations. So you need to compute this. It looks a small equation, but it's a very complex equation as you start for creating a code for this and running it on a simulator. So what if this code has been now written for an hardware, and what we did is we wrote a code for this and we put it onto hardware so that it plots. And not only that, we wanted to understand when I run this code, how much is the power consumption of the hardware. That means the digital circuit. So we just even deployed this to run it on a 6-core. So that we understand, like, one of the core is switched on or off, like how much is the power consumption. So the whole setup was actually planned and ported onto the hardware. So when I say hardware, so this goes into the emulator while we capture this image through our multimedia capture, so that we actually post-process the image. So this is what, just wanted to give a demo later on as a time permits. So we have had an UPF also. That means to analyze the power activity of this particular code when it is running on the hardware. So for example, if you take your design and a test is now synthesized onto the emulator, and your test bench, which is a transactor, is now ported onto your host machine. So this is how it looks, the complete environment of an emulation setup. So you will create a proxy and communicate with your BFM, as that's called as bus functional model, whether it can be an SV based UVM or a direct programming language, means interface, which we call as a DPI, which can be C based or an SV based. So this is how we try to communicate and extract the data, image data from the DOT onto your host machine and plot it and post process those image. So this is a small equation, but it's so complex that it takes time even when you run onto an emulator. So this is the RTL code of the Mandelbrot, and we extract those X and Y position, which is actually the pixel data that it gets plotted. And not only that, the emulator allows you to see the logical representation of the code that you have written in terms of flops or AND gate or XOR or NOR, and then you can see the flop, and you can correlate whatever the code is written, and that code gets into in real silicon how those logics would be, and the way it's going to communicate with your memory. If you see, this is a RAM. It says all the pixel that has been extracted is now returned to a RAM, so that can be extracted back and plotted as an image. So the emulator allows you to view your RTL code as well as see the waveform and see the data and also the equivalent logic onto it. So this is where the emulation gives you an advantage, which if you look, it is more like in a simulation, and you could also be able to do a line breakpoint the way you do it on your C or simulation, where you put a breakpoint at certain line, and then you start debugging what's really happening on your design. So this way, the software should be able to do this while it's actually running on the hardware. So when it's running on the hardware, the emulator has to stop the clock, and it has to jump as per the data, the way you are going to be moving or putting breakpoints to stop and start your clocks. And during this time, you should be able to have the same simulation kind of environment to start and stop the clock. And also when you start or stop the clock, you can do a lot of other activities like resetting your other signals or uploading or preloading the memories or view the memory and see whether is the actual activity is being updated, or if not, you can stop and do some manipulation in your design and do it. So this is exactly the way you do it in your code can be also done on the emulator with the simulation GUI in the front end, but you're actually running the whole of this on the hardware. So it gives you a feel that the complete features that is on the simulator is now on the hardware. So that's where the hardware becomes much more user friendly in terms of hardware assisted verification. I just wanted to give a little bit glimpse more onto these hardware. What is this hardware? So we saw there was a chip which, takes up this code and ports onto the hardware, gives you a realization as if it's a real code or a real silicon that is there for the given hardware. So we have those chips on a particular board, but as you wanted to increase the size of your design, we just increase the number of board. So this board has a capacity of 16 million gate of each board, but as we increase the number of board, we need a bigger boxes, and bigger boxes, and the bigger boxes goes in like this. You can go up to 2 billion gates. So if you see, the whole of this is just a box, but it has a rack of these boards internally. So the higher the number of capacity it goes, we start increasing the number of boards in these boxes. So this way, when you actually switch on and you run your design, it just gives you as if this a bigger design is just sitting on a single FPGA and running it. So that's the feel that it gives when you actually run on a custom chip emulators onto it. So now, since as we also saw that design size are bigger and bigger, it can be scaled up from a 16 million gate up to like a 15 billion gate. And this is the hardware. As the bigger the hardware it goes, the more the capacity can be validated. Similarly, as what you are actually running on a simulators. So it has also a lot of memory on the chip as well as on the board, so that the memories that is part of a design can be mapped directly to the memories instead of using the logical arrays, so that you save a lot of logical arrays or a capacity with reference to your design. Else, if your memory starts using a logical arrays, then you need more bigger capacity of your hardware, which in turn may not be an efficient way of validation. So it is always best is to map your memories directly to the equivalent memories on the hardware, so that it saves good lot of time, and also the performance increases when you actually run your logics on your actual logical gates on your hardware. So this is where the hardware looks this, but with having this hardware and software to compile, what all it should be able to give the benefits when we have a variety, or different types of different types of verifications that we have today. So one is like, when you want to have an emulator, you need to make sure that it gives you a better performance, and it should be able to scalable, whether it's a smaller design or it's a bigger design. And it should be able to fast adoption in the sense like it should be able to adopt any type of methodologies or any type of coding that is there, should be able to easily integrate onto your hardware and be able to run it. So that's where is a fast adoption and of any methodology. So we will actually look a little bit more in detail about these topics as we go on to see how emulation is really helping out the industries with reference to the challenges that they have to get the chip out faster when they have a different types of test benches or a different type of methodologies they wanted to validate. So when I say with the emulator that we have with the chip that we have developed, we need to have a software which can consume the RTL code that has been written, whether it is an Verilog or VHDL or it's a gate level netlist, along with your UPF, that's for the power, and even for design for test, like that's for your DFT design or assertions coverage. If you see, these are all the things that you actually do it on the simulation is easily acceptable, and it should be synthesizable. We synthesize all the assertion coverage as per the industry standards, and we do synthesize some of the behavioral codes so that it can be converted into the synthesized onto the hardware and run much faster. So anything that goes onto the hardware will run faster in the sense is because it's logically being represented and communicates, it's powered on and it runs much faster than it is actually trying to compute like a simulator. So if you see, the compiler takes care of the RTL code given and automatically synthesizes to the logical data that is being written, and it is ready to be ported onto the hardware for further debug. it is completely automated and has accurately, means compiles accurately with automated partitioning and pin boxing is also done automatically. There's no timing issues. It's all works on as a cycle-based simulator, but it does save the data of every node points, so it becomes like an hybrid, and it also communicates with your host machine with a optimized bandwidth that's available between the communication between your hardware and software. And not only that, most of the time people have written, have their RTL ready for getting into the silicon. So they create a gate level netlist, and we could also run gate level netlist further onto the hardware, which where we say the gate level netlist is very much accurate, or it can correlate with a higher currency when it is, which is said to be near to the silicon. And you can run those type of complex validation onto the hardware much faster. So it also, wherein the hardware assisted verification helps in validating uh, gate level netlist too. But only thing is that it can only do functional verification, and it cannot be doing, it does not support any of your timing analysis. So the compilation flow is similar to an FPGA flow, wherein it does analysis and synthesis, and does place and route and place and route for the given chip, and it is ready. It creates a database which can be ported, and then also creates an environment wherein it can replay the waveforms once it is captured as an offline for your environment. So this is completely a single process, or you can use a form to compile this as a distributed flow, wherein it reduces your hour of compile time when you run into the uh, in a distributed form. So this way, bigger designs can be compiled much faster, and it does supports most of your encrypted code too, but it should be encrypted as per the MED-IEEE standard. And if it is MED-IEEE encrypted, so it does support the encryption code also, and it doesn't depend upon any of the vendor software. It's completely independent of the vendor software, so everything is mentor based. So this works similarly with the other technology in the market. So most of the custom chip uh, emulators have their own softwares because they have their own chip. Similarly, they may have for Altera or Xilinx, they have their own tool to their partitioning. So similarly, we have the same in for the Veloci too. So this way, any issues happens, it gets as a part of the support, and be able to optimize and continuously enhance in terms of capacity or runtime, and also for supporting any new language constructs that comes up as the time goes on. So it gives you all the similar kind of features, like your simulator. As I said, you can stop the clock, start the clock, load triggers, and at a trigger point you can stop the clock, manipulate, and do read write registers, and then rerun it again, and also capture waveform. Similarly, what you do it in your simulators only, and it can immediately upload the waveforms once the waveform. I mean, once the emulator released, you can offline debug your waveform as what you are actually doing it in the simulator. It gives you completely 100% visibility. That means you should be able to look at the waveforms for all the signal nodes that's been there in your design. So we have an hardware which works like a simulator, and which is actually complementing your FPGA and a simulator. But simulation does a lot of other activities, like it's assertions, coverage, power, lot many things. But again, there's a limitation that cannot be done on an FPGA prototyping. But can emulation do it? Yes, emulation can do. There are different modes of emulation, wherein it can take the test benches as a different test benches, wherein the test bench can be the real stimulus that you can give, in the sense like you can pass in the real data uh, to the your DOT, where your DOT is actually sitting onto the hardware, or you can use a SV test bench or a C-based test bench to drive in stimulus. which we call as a transaction-based acceleration. Or else, you have a lot of peripherals, because nowadays SOCs has a lot of peripherals like USB, Ethernet, or PCIe. So those, if you have to validate, you can have a virtual solution for those. And not only that, with having all of this running on your hardware, you can also do a software validation. That means you can port your Linux or Windows environment onto it and run application, while your actual HDL code is sitting on your hardware, and you're validating as if you're validating your actual SOC just before it goes into your silicon, and completely validate your both your hardware as well as your software, and gives you a complete validation on hardware platform, where the platform is one, but you can use all kinds of mode of emulation. So you don't need to configure your hardware. Hardware stays as it is and doesn't need, it is just more of your methodologies, the way it goes in. So your DOT actually sits onto the emulator, which is synthesizable, which will be part of your silicon, and your test bench will sit on your host and communicates with between your hardware and software through a copper wire, or nowadays it's all optical fibers. So the data communicates between your test bench, which is running on your host machine, and stimulus sent to your DOT through the copper wire. So now the data goes in and out. So the way it goes here as a part of your stimulus, it all depends whether you can push all of your stimulus test bench on your hardware and make it standalone, or else there are a lot of behavioral codes which cannot be synthesized. It's on your host machines. So this way it does communicate in parallelly, and helps you out in a debug like start stop, as I said. And not only that, if your bandwidth is not enough, you can always increase the bandwidth in case if you have a lot of peripherals connected to it, so that all the peripherals can have its own bandwidth, channel and communicate and run much faster, and execute your long test in a shorter period. With this, you have the complete flexibility of using the platform faster. So let's take a few modes of emulation. So I would just say start with a transaction based. So when I say transaction based, is normally most of your design has a top and your DOT, and your DOT would be interacting with your test bench at a pin level, or I would just say signal level communication connections. But when you go port this onto an emulator, most of the time the design which is there sitting on your DOT is on your hardware, and your test bench sitting on your host machine. Now the host machine is your software side, but it has to communicate with your design on your emulator. For every clock edge, it needs to be communicating between your emulator and the host machine. So there's a huge latency, and your performance goes down. So in such a cases is where we call as the transactions, wherein you actually push most of your peripherals or synthesizable part onto the hardware, and communicate with your test bench only on a required basis, like task or functions, or you call or capture the data only when it's required, is where we call as writing transactors for BFMs for your designs. So wherein all your untimed part of transactions sitting on your test bench, and timed part of where you use clocks is sitting on the hardware, and you communicate between your test bench and the emulator. So this gives you has a co-emulation, and which improves performance much faster. So for example, this is how the flow looks like. Say, for example, the test bench is sitting on in your simulation environment, both are sitting on your host machine. Now, if you take the DOT, that's your design onto the hardware, since it's much faster, it is already converted into gate level logics on the hardware embedded. So it just runs faster. But while your test bench is sitting on your host machine, so communicating between these two, you might not get a good performance. But as soon as you make it a transaction based, wherein you call the transactions, or you call the data or stimulus only as when required, and that way your communications of every clock edge is reduced, and you get a better high performance, is what we call as transaction based emulation. So this way you see the DOT sitting on hardware and your test bench sitting on your host machine, and through your transaction layer, which is actually a code as a transactor, which helps you to communicate between your hardware and software, which will increase your throughput and performance and get the complete test running much faster. So just to give you an idea what is a transactor and device that needs to communicate. So normally when you have a different media that's going to run your duty and there's another media like the software, the host machine. So then there needs a transactor to be developed or the tool will create as per the design that you have written. For example, duty is written in your RTL code. Test bench can be written in high level language, whether it's like a system C, UVM or SV, and it communicates with your using a transactor which is being created using an APIs. And this APIs communicate with your DUT at a pin level communications like this. And then so if these will now interact with your BFMs, which is actually written using interfaces or communicates with a class proxy, wherein the BFMs can work like a drivers at an cycle accurate clock stimulus to the DOT, as well as you can drive. There are monitors which can collect the same cycle accurate clock data from the DOT itself in a way where you can actually have those BFMs also be synthesized onto the hardware by using an XRTL coding style, which is something like an Mentor proprietary, where it makes your most of your BFMs synthesizable and make sure that this is written in XRTL and all your transactor based your proxy, if it's written in C or C+, is sitting running on your host, and these are communicated with as an inbound and outbound communications using your task or functions calls, or through your interfaces under the hood, which communicates between your hardware and software. So this is what we call as a transactors, and the transactors are the ones which communicate between your duty and your test bench, which is helpful, works both for your simulation as well as for your emulation too. And this is where we wanted to now accelerate your whole of your design to run much faster. But with the advancement of the test benches, we saw that Ruchir also said that most of them started using the UVM based test benches, where people start using because of the random constraints that can give you a higher number of stimulus and to verify your DOT. So it could, we do also support, but UVM has a lot of class-based constructs which cannot be synthesized, which are dynamic in nature. So we do have a way of partitioning this design. Just say, like, for example, if this is like this, if you see this is an example of a UVM or OVM test bench where you have stimulus, which is driving the driver, and also a responder, which is driving your slave, which is part of your test bench. It actually collects the data from the monitor for your scoreboard. So whatever it's going to send and what is going to be received at the monitor level, so that you can match those data and get your scoreboard and also get your coverage. And this is the complete way, just a quick look of like how your UVM environment or OVM environment would look. But now to port such type of environment onto the hardware, we try to partition the design into two top, wherein at a place of drivers and monitors or responders, we have used, there will be a lot of tasks and functions. We can write a BFMs on top of it using a system verilog interfaces to split the design and have part of this design running onto the hardware, while your all the other part of it running onto the software. So this way you should be able to easily port your UVM designs on your emulation environment, is where we call as hardware accelerated for UVM based or an advanced verification environment. So wherein all the proxies, as I said, proxy classes or non-synthesizable or dynamic in nature will always sit onto the host machine. And the same environment, whatever you have created, will work both in not only in emulation, will also work into simulation. So you don't need to really change the test bench, that because this is to be going on to communicating with the hardware, with the duty which is sitting on the hardware. So it doesn't need to do that. It should work for both simulation as well as emulation, and you have the same test bench for both emulation and verification. So if you see, we do cover all kinds of test bench, whether it's system C, C++, or UVM or SV, and which actually runs on the host machines. As I said, we support good lot of constructs like $display or $random and all of these constructs and initial blocks, and even your SV assertions can be synthesized so that most of your design actually has been ported onto the hardware, and you get a good lot of acceleration. That means your long test can be shortened by running it on the hardware. So we'll look into the second mode of emulation, what we call as in-circuit. So earlier we were talking more on the test bench, where you actually have your stimulus written in C, C++, UVM on test bench, while now we will actually try to see how is a different test benches, like when you have in-circuit emulation. Just a second, I'm just trying to this. Sorry about that. So is what we call as in-circuit, wherein you can actually give a direct stimulus, a live stimulus itself as a stimulus for your design. And this is very much required to analyze the real world environment, something like, where you have your design as a DOT and connects to your actual peripherals. And these IOs and the details of the data that is going to communicate will be live from the stimulus, that you can plug in Ethernet or USB at an L5 to your DOT and try to send that as itself as a stimulus to your DOT and verify your whole environment. And also, not only that, you can even port your software on top of it. You can use JTAG to debug your software and validate the whole thing. Only thing, the difference in circuit is that you are now going to pass your live stimulus for your DUT, which is running on the environment, on your hardware. Say, for example, if I take an PCIe, so we will use a PCIe speed adapter to communicate with a real, pass the real stimulus to your DUT. So we interact your module based IOs at the real physical IOs that is available on the hardware, and connect that to your speed adapter to your real host machine, wherein as soon as you have the PCIe endpoint module, which is in your part of your duty, as soon as you switch on your hardware and you start running your clocks, you will see that there's a new PCIe card found in your host machine, and that way you can configure or run your stack on it or software stack on it and validate. So what's exactly is happening is you're running your software, and the software stimulus is going to the hardware as a live stimulus to your DOT. So this way you can actually verify the real world environment. But the real world environment is running in the faster speed, while this might be running into a lower speed. So that's where the speed bridge or speed adapter has been used to communicate, to make the speed reduce, or, I would say it's like a buffer the data and send the values to the emulator. But this is where we actually have a physical box connected. But today's world, as we see that today's been it's the way it's going on with this pandemic, we always look for virtual. So while we thought of this very much earlier, to have all these peripherals to be part of the virtual is because we wanted to have these peripherals, instead of sitting in the lab and connected to your hardware, we thought of making it virtual so that it can be accessed anywhere from across the global and work like as a data center, is because you can have the emulator of the data center, and instead of connecting the real peripherals, we will have a virtual model running onto it. That means it will become a soft model of a peripheral and can be run on a software on the host machine wherever it has been connected. And with running that software, which is a soft model of your peripheral, which will act as if it's a real world, or gives you a real feeling of the exact peripheral. Like, for example, if you have a PCI root complex, you will be having the model, and the OS or the model that we have a PCI is in the soft model running in the host machine. And you'll also have a protocol analyzer or a monitor to watch that but this is not the real hardware. But you will have an equivalent soft model running it on a QEMU layer on your host machine and communicate with the hardware as a transaction base. So these are all built into it. It is just that you'll have to hook or call this transactions or call this module instantiated in the hardware. So this way you really don't need those peripherals that you need to validate, can be now made as a virtual, and you can call as a soft models of each of these peripherals and communicate between your hardware and software and validate all of your peripherals. Similarly, like what you were actually doing it when you wanted to, this is just an example for PCIe. Like this, you can do it for Ethernet or USB or display or HDMI, any of this port, the way you want to do it can be done on the virtual. The way it looks is the DUT sits on your hardware and you have a nullify, and the software stack, which is actually running on the host machines, communicates between each other through a transaction based layer. So this way you also get a backdoor analysis, backdoor access for your memories or collecting the registers and everything, which can be easily run onto the, it's validated by running your software and validate your hardware or the complete peripheral that's been communicated, it's been part of your SOC. So if you see that this gives you a very better remote access than having a virtual, is because in a virtual in a physical environment, you need somebody to be in the lab, and whenever there's a configuration changes happens, you need to switch off and switch on the hardware. So that saves a good lot of time when you actually go on to the uh, virtual mode. So that's where we say is de-risk the schedules by having lesser hardware, and also in case if the designs are big or there's a lot of projects and validation is high, the virtual model becomes much more user friendly, is because everybody have their own configuration. They can just disconnect from the emulator and run it directly with their own configuration. So now that we have connected to the peripherals and your SOC is there, we need to now validate the software running onto the SOC. So running the software onto it is like you actually now trying to run your OS, which will actually consume a lot of your CPUs that has been written as a RTL code now is sitting on your emulator. Like for example, if this is a design where you have a core and PCIe and all the peripherals, now you can use a JTAG interface as a physical JTAG to communicate and debug or part of your validation, or else you can also have a virtual JTAG that can be worked. Sorry, that can be virtual JTAG that can be, instead of using the physical, we can use a virtual JTAG to communicate between your CPU on your test bench or CPU and your debugger, so that you can extract all the information of your registers or the cache registers or cache memory data that has been running on your host machine. So there is also, as I'm just talking more on how the emulation has been now been useful in validating the way you actually do it in software. So now, since that it has been using an hardware, so people need to use the hardware for SOC verification. Now they're porting their software, but once they run their software, they are not now validating the functionality of the SOC, but they're validating their software. So the software engineers or the application engineers who actually write applications on these software for an SOC that they are designing will now try to extract only the information that has been running on their cores with all the CPU registers and memories and what's happening. And when they run their application or when they run the software with their form, with their test, they might find some hang or some issues that is needs to be debugged. So that time the hardware is being locked. In case if they're using JTAG, they are completely locked. If they go for a method called as codelink, which is a non-intrusive method, that means it will just extract the data and create a big log file, which can be offline, to pull out the data and open it in a codelink software where they can actually see the hardware signals as well as the C language or the code that is being, which is being loaded onto the core as a software, core onto the software, and also the assembly language, and all can be cross-verified each other as a complete environment, which is actually gives the complete hold for a software engineer to run it much faster on the hardware. The only thing that it becomes more efficient is that when it is in the connected to JTAG, one has to be waiting till they finish their test. While if it is a code link, which is a non-intrusive, they can just keep run their test, finish their test, and release the hardware and bring back their database offline and debug. So this way, the emulation helps in very efficient way of debug for not only for the software, for the hardware engineers also. So this way they can efficiently use the hardware and get complete information about how the design has been running onto it and what's during the run, what exactly it's happening and all the changes in the registers, that they can put their own breakpoints offline and then debug with reference to their actual code, and also cross verify your hardware data that has been extracted. So there are a lot of advanced features. There's a good lot of features like IP replay, backup replay features, and check bench restore. Like you change something in your test bench to just part of your debug. You don't need the DUT be recompiled every time. You can just only have once change in your test bench and rerun it multiple times and capture those. And similarly, you can do the vice versa, like the change, have one small change on the DUT just for a validation purpose. You can always do use a checkpoint where it can run it for certain time, put a checkpoint, and then run it later on. I mean, run further. But when you come back, you can run at those checkpoint points and rerun that particular point to actually see what's really happening on the certain later of time of your test. Because most of the time, the long runs that you run, long runs for the test that you run will be always run on an emulation. The short runs can be always run on simulator, but the long runs when you do on emulators, it shortens your time. But when you start running with OS and a lot of other things, when you're running for long hours and something breaks, it's always a difficulty to go back and rerun it in the same place. So there's good lot of features using this checkpoint restores or a backup replay. For example, if I take one of the advanced features of backup replay is that you can always run for long run and capture the bug or restart your run from at one particular stage. So it debugs with the hardware as an emulator, hardware assisted verification, gives you the complete visibility without any impact on the capacity, and also gives you a feature of generating the waveforms on the fly, similarly the way you do it in simulators, and it will be much faster without having any latencies, because it is just like a one-way call. You just keep streaming the data out to your host machine. And since the hardware is connected to your host machine through your optical fibers, the channels, the bandwidth channel is very high, so that huge data can be transferred back to your host machine. So only thing is that DUT, I mean the hardware, the host machine should have a good memory capacity to capture long waveforms. So we do have a visualizer that's again part of the debug. But so if you have these tools as a overall of environment along with your hardware, it gives you much more hold for your bring up and debug your complete SOC much faster. So for example, just to give you to give an example, if you say like you run your test for 10 hours, and at the nth hour of a time, say like at the ninth hour, there is some issues found. It could be a bug or a drop in a packet. But next time when you're going to run, you don't need to run for 10 hours. Instead of that, you can start at the ninth hour itself and rerun from that particular point and do a breakpoints and go step by step, or enable a lot of monitors like display statements and everything. And you can start going step by step and find out where exactly the issues. Now this way you save 9 hours of time whenever you have to run next time and you have found some issues, which is more deters mistake, and it is repeatable issues that can be debugged. So this way the debuggability is high in terms of emulation, which will help you resolve and debug issues and fix it much faster on an emulator. That's where the advantage of emulator comes into picture, with a different kind of emulation, modes of emulation, whether the test bench can be UVM or live stimulus. But this is where it limits to your hardware acceleration, where an emulator is now working as a simulator, but you're only doing a functional verification. But once you're going to go a little bit more, like, want to do a power analysis or assertions or DFT, which actually, again, you have to go back to your simulators. But now the emulation has been advanced to a level where it can now start synthesizing a lot of these advanced verification components onto the emulator. So we created that has two different apps just to make sure that it can be categorized and it is more customizable for the platform. So this is where what we did is we created apps called as Veloci apps. For example, one is like power. So we can do a low power analysis on an emulator. So that's where it gives you a better advantage. And moreover, low power is very important in the industry is that, as the technology goes smaller and smaller in terms of die size, the power consumption is more, but because of the power is high, the chip gets heated. So they have to have a better management of power and so that the equipments or the application, the gadgets that we use doesn't get more heated. So this way, and also there's a lot of standards whenever the components or the gadgets being released, has to go with the industry standards so that they are more saving the power as well as making sure that equipment or the hardware that you use is not affecting the humans or affecting the life. So this way, demand for power management is very high in the industry with a lot of applications that we have already seen that like, AI, ML and automotive data center, mobile or CPU, GPU, wherein the power factor becomes more high in terms of power, performance, and the area of the die becomes a merit of the analysis. And with a lot of heterogeneous multiprocessing systems as driving is again gets focused onto the power. So with all these complexities, power has become an important task that needs to be verified, wherein we need to identify the hotspots on your code. That means you have written a code, but which particular test or which particular block is getting heated more in the sense because of some free running clocks or because of type of coding style where there's a lot of power is being computed. And when I say power, because of code has nothing but the toggling information that's happening or the switching information that's happening on your SOC because of the code, the way it is written. And how power is consumed with reference to my toggling means is that whenever it is on high, there is a power is used. So what we call as Q is equal to CV, the way the capacitance and the voltage comes into picture so that there is a power consumption or the wattage comes into picture in which you actually try to get heated because there's more current flowing into it and more current flows into it whenever the switching is going high. So many times it goes high, there is always more power has been used and then that becomes heater. So this how I'm just trying to give an idea like how your signals or your coding can impact the number of times you going to switch it. For example, if you have a free running clock always keeps going toggling and then the number of times it goes high, that particular model might get heated up. So to avoid those type of things, they put as a gated clock and then that's how they do it. So those type of codings are being done and to have such type of issues being seen in an SOC and we need a solution that needs to fix that. And not only that, there is a lot of applications when you run like, gaming or running or a lot of high performance applications. Yeah, as I said, gaming or, even processing a huge lot of data. There is the lot of toggling activity or the CPU or your SOC is being consumed wherein it actually gets heated up. So to avoid all those things, they need some type of solutions wherein they can analyze huge data, compute it, and use some power tools to analyze those and tell us which particular block of the code has been, heated or hotspots are there, and find out that. So that's where we have emulation. Like Veloci has what we call as a power app, which can actually extract the information of the activity plot and gives you generates a file called a switching activity file. It can stream out or it can create a file and pass it to the power tools to give us the actual power numbers wherein it can actually tell you how much is the power consumption from the power tool. And not only that, you can also switch on and switch off the modules and try to see when I switch off and switch on some of the components in your SOC and how is the power efficiency. So to do all these things is where we need to support for low power verification called as UPF. So all these things can be easily ported onto the emulator, and emulation should support. That gives you an added advantage of having an emulator to validate this, is because running UPF and your functional verification on a simulator again becomes more stressful. So that's where the emulator comes into a picture and can validate these kind of complex applications, or I would say complex verification by itself. So now you can, as I said, it supports UPF, so you can switch off and switch on some part of your model. For example, when you take a mobile and you keep looking at the video, so the multimedia is being used, display, and your video is running. But as soon as you get a call, you need to switch off the display and have your modem on. So that way you're trying to switch off your display for your video, but you're having the display only for the call. So you save good lot of power over there, or both are on. That means there's more activity happening on your mobile. So this way, when you switch off and switch on, and when you swap between different modes of your device, it should retrieve back and continue the same. So as soon as the power call is off, then you back and you should resume your video to continue. So these type of validation is required, and wherein you can try to isolate and create multiple domains of your model so that you can save power whenever there's one activity required, while others are not used, can be switched off and save more power. So these type of power managements can be validated onto the hardware, and you can generate a lot of files or the data that can be computed for the power tool. So normally they use save file, which we call a switching activity information, and which can be part for this RTL or for the gate level, or it can be, you can generate an FSDB to calculate an average, peak power. So this way, now you're extracting a huge data, and that itself also, that data also is like a big, huge waveform. And that is in the format of, say, for FSTP. But when you're having a bigger file for your bigger design, and since you're going to run for long hours of your test, then automatically the file sizes or the computed data for every clock cycle has been stored into a file, and that file size becomes big. So instead of saving it on the hard disk, you can start streaming it in parallelly to the power tools, wherein it can immediately start analyzing using your power library and give you out a peak, average peak power. So this way the emulation helps the industry to actually help in power analysis, wherein the complete cycle of getting the activity plot for million cycles, and then the power estimation goes into the using the power tool, and then power tool gives you some optimization solutions, and then again back into the hardware and verify the complete. Now what industry needs is to have a seamless communication between your emulation, and then goes back into your power tool, and the changes backs into your hardware. So this way, this saves and improves your power validation for your given SOC. But now what happens is, when you have your SOC and then you also have your software running onto it, then it becomes hotter. So this way, the complete software you're running and your power analysis is also done. So the whole of this solution is by itself is available, and it is easier to do it on a hardware than running it on the software, because you not only extract huge data for your computation of power, but you're now also extracting huge data when you actually run your OS on top of it and run a lot of these applications for your benchmarks. So this is how it saves emulation, or an hardware assisted verification saves a lot of time in verification of your hardware or your SOC for the power activity. So there's also a DFT. So we call as design for test, like, normally once the gate level is done, and then people just before going into the silicon, they wanted to understand what is the yield of it, like, how much chances that some of the components fails, like how much is the chance it fails, like how much it could be recovered back, or how those tests can be validated when it is running in a gate level netlist. But if you're running a gate level netlist on a simulator for a given type of test, it takes huge lot of time on a simulation. But the same thing, if you can run it on an emulator, it runs much faster, is because the gate level netlist gets mapped to equivalently onto the hardware, and you should be able to share, import the style file onto the emulator and run much faster comparatively like what used to run it into the simulator. And if you see, there's a huge improvement when you run between simulation and emulation. So this way, hardware accelerator emulator not only helps in functional verification, but also in advanced verification, like power, as I said, for DFT. Similarly, for fuse applications, wherein which is more important today, as we said, automotive and Milero customers who have a dependency of these electronic components or the SOCs in their applications. They wanted to understand like what happens to their SOCs when during the device is running and something goes wrong because of some radiation, or somebody is trying to hack and change, or because of of the ambient condition. If the working design goes wrong, and how fast they can retrieve and recover it. For example, somebody, if there's an electronic device which is going to control the brakes, and because due to some other issue, one of the bit goes wrong, but that is the bit which is actually controls your brake, so it would automatically brake, or it may not brake, which will end up into a life disaster. So what they do is they do inject errors onto those nodes using a fault injection app, and to see when there's an error and how the design recovers back and reruns immediately within a very small short of time, so that whenever such incidents are there, it just recovers back, and then the brake application works as it has been designed to brake when the brake pedal has been pressed. So this way, these type of validation is used, especially, as I said, for all the kinds of life-based equipments like automotive and Milero. Even in the space grades is being used a lot of this, is because because of radiations, things might go wrong. That would impact some of the nodes which was supposed to take a 0, it becomes 1, or it might, they call it stuck at 0, stuck at 1, or it goes wrong. So when it goes wrong, how fast they will be able to recover and reuse those SOCs as it is. If not, if it goes bad, it goes bad, so nothing can be done. So at least if we have a recovery circuit on it, and then these things goes wrong and the recovery circuit works, it helps in reusable, or becomes more efficient use of the SOC. So hence helps you in validating the whole of these environment on those hardware, and the emulations are all now certified with ISO 26262 standards, which is a standard which came up as a part of user or part of the industry, saying that it should go through the standard. And as what Ruchir also was explaining today morning, that there is a standard now which needs to be compliant. And so hardware accelerated verification is now these standards, so that these type of fault validations can be done. And along with this, I think next comes is the coverage, wherein you might have used this as a part of functional coverage or a code coverage to analyze or debug your codes that is being written, and validate it much faster without using your waveform. You can immediately say, okay, this has gone wrong. If this is true, then assert it. If not, fail. Those kind of assertions of formal verification. And you can also make sure that the number of lines of code that you've written is actually being used, so that when it gets synthesized, it just makes sure that the code is part of your hardware. And not only that, you also make sure that all the code that is written has covers with reference to all the tests, and gives you an idea that all the tests that has been run is covering all the components that has been written, and in turn gives you a complete coverage saying that yes, my SOC is now good and is as per the specs. So this way, having all your designs with these constructs in your code also be easily ported onto the emulator, and extract a database like a universal code database, which can be merged or with multiple tests and gives you out the complete information, and wherein when you're trying to analyze huge data and gives you out much faster results. So this way, hardware accelerated helps you out in coverage and closure of your functionality of your SOC, uh, which normally you do it on simulation and it takes good lot of time, while emulator does helps you out. And this is also ISO 2626 standards complaints. So with this, if you see, the hardware could do good lot of verification, not only functional but also advanced verifications, and the whole of these things that can be run on a simulator can be now run on emulator for the full chip validation. But now this full chip validation is running, and since this is running at an enterprise level where multiple people can use it at the same time, and can be also be used across the geography, what happens is there is a lot of many users in the queue. So to manage the number of jobs in the queue, so there is also a solution that the emulator can handle the number of jobs or the number of tests that it needs to run. But it can also do a way that if there is some job which is urgent, which can actually automatically park one of the job and finish the high priority job, and then put back your current job that has been running, is what we call as parking. Is similar something, the concept is of suspend and resume. So this way, the designs that needs to be taped out faster or something that needs to be validated can be also pushed within the hardware queues and managed. So the overall, the emulator has grown to a way that it can manage not only your functional verification, but also manage a lot of your different designs or different blocks of tests that has been run by multiple engineers. And this way, Veloci also is grown to the same level, and emulator also is grown to to a level where it can manage the whole of verification in an organization or in the flow of verification. So I would just say this is how the complete platform it looks. So it's the same hardware, it's the same one single software, and it has a lot of applications that it can run on top of it with any mode of emulation, whether it is a virtual lab, in circuit simulation, UVM, or have the software. It's the same OS. So OS is nothing but it's a software. It's a single software. You don't need to have multiple softwares. So you have a single software, you just enable power, enable assertions, or the switches you just add. So it takes care of it. And hardware is there, it is switched on and it is lying. You just need to tell what is the hardware name. That's it. That is enough. It automatically takes care of compile and does for the plan. It compiles a database for the platform. It doesn't need to tell how many boards and what it is there. The tool or the environment takes care of the whole of thing. So this way, the hardware now becomes a complete verification platform, whether if you want to do it for power assertions or software debug, or you have a fault or DFT. And there is a good lot of this covers good lot of domains for validation. So if you see Veloci plus solutions, instead of saying Veloci, I would say like hardware assisted emulator plus solutions and apps, covers the complete vertical market, whether it is in Milero or FPGA or mobile, cellular, networking, storage. It does covers all kinds of application, but it's the same software, same hardware. There's no need to configure. It is just is a part of your code or different type of test bench codes that it supports the whole as it is. So that way, emulation becomes more important as a part of verification. And there are a lot of libraries now written for emulation friendly. So most of your IPs are now become emulation friendly in the sense like these are all synthesizable IPs, which helps you in porting the whole SOC onto your hardware and run it onto the emulator. So nowadays, most of the IPs that comes with the accelerated VAP for emulation, and the same IPs also works for the simulation. So this gives you a faster bring up and easy to use and faster validation. And I said with all those IPs are available, so it can work with the memories as a part of soft model, or any of the IPs, whether it's UVM based or System C or IEEE standard, I mean, say system Verilog, you can use live stimulus using the speed bridges, or you can use a virtual lab for of these peripherals. So this makes your complete as a complete solution for your project using an hardware just before you wanted to get into the software. So just one last as a summary is that the market now it's trying to push with reference to AML storage and 5G. It's trying to push the hardware accelerated verification a more important in the part of the verification, and even like Siemens, which is also a bigger company, is investing a lot in development. So Veloci as an example, since it's from Mentors, we do support all kinds of high value Veloci applications for power DFT. So since we have our own superior architecture, we use our own chip, and it has a highly scalable capacity and performance. So it should is very well aligned with the market changes, and we keep doing those changes and enhance as per the requirement. So this becomes easier is because we have our own chip. So that way we can manipulate or keep enhancing the needs of the industry and market. Overall, hardware accelerated emulation can be used from the block level. It doesn't need to be that it should go only on the system level or anything. It can be used from the block level or complete SOC using with the peripherals. It can be used from the beginning to the end of the cycle. So that's how the hardware assisted verification is important, and that's helping the industry to get the chips tape out much faster than what used to be earlier, and make sure it is as much as possible is the bugs free, and run many of these onto the hardware. So that's it from my side. So I'm open to the questions.
Thank you, sir.
I would, I don't know, I just need, how do I get, okay, chat window. Just trying to find.
All the participants are requested to please give their questions in the question answer section, please.
I'm not able to see any questions.
So there is a question that RTL code can be written in Xilinx instead of Quartus.
Yeah, so the RTL is it's an HTL language. It can be written for Quartus or for any of it's a coding style. It can be written for any, hardware, whether it's a Quartus or it's an Altera or any of the emulators. But RTL is a very basic written as an hardware description language.
So there is another question, sir. Can the software development part can be done on emulator like FPGA prototyping?
Yes.
Thank you, sir.
Okay, I'm just unshared it so that I can just see the questions. So any insights on how close?
Sir, there are 3 dots in the screen.
Okay.
Yeah, so if you click there, there is an option question and answers at the top.
Oh, okay. Yeah, I got that. I'm just trying to see at how much order of magnitude is PCIe verification is faster compared to the wire. Yeah, it should be very much near to it. I mean, there is a question which says by how much order of magnitude is PCIe verification faster compared to the wired based know, connection. That means when instead of having the real hardware, how fast you can do it on the software based, it'll be faster. It may not be same as it is, but it'll be near to the what you are actually doing. So you would get the same performance. Insight how close the power numbers from Veloci app approach actually. So we have seen 2 to 5% difference. That's as per the industry standards. When you try, okay, there's a question saying is how close the power numbers from Veloci app approach is actually. So we have seen with the customers like between 2 to 5% differences, which has been accepted as a part of the industry standard. But the accuracy is always to achieve 100%, and we do those as per the user changes. What exactly is a block level verification? Block level, what is exactly is block level verification? When I mean to say block level verification is a small IP or a small component of your SOC. We can have a demo quickly. Question maybe working say 14. How does it gives a correct result? So there's a good question here, which I would like to just highlight this. Hardware emulation may be working, say 14 nanometer. How does it gives correct results for 7 nanometers? So emulation has purely a functional verification. It doesn't depend upon any of the technology, but it does depend upon the technology libraries, whether it's 14 or 7. So it just looks only for the digital part of the libraries. So you should find the same results whether it is 14 or 7. But there are a lot of analog or timing analysis that might vary. But emulation as a hardware emulator works mainly for on functional verification. So I'm not typing the answer, but I'm just reading out some of these questions. Okay, this is one more question. As I understood, his emulation is used for only functional verification. So it cannot promise timing analysis. That is true. So it can only do functional verification and it cannot do timing. That is true. So at least once you finish your functional verification, you're sure that your code or your SOC is good with the functional. And when you run for your timing test, you can easily isolate that whatever the issue comes is because the timing, not for the functional. How can we say the design is bug free? Yes, it's just again, when they say 100% coverage or 100% test, whatever is written, they say they have completed it, but it's all depends upon your stimulus or the type of test you're done. Can we calculate the power? Yes. Can we calculate the power in the model sim as well as Xilinx? I think. In SOC, is SOC verification or RTL verification same? Yes. SOC is the full chip, RTL is the code for it. Can you address fault coverage? So fault coverage is something that you run 100 tests and find 100 faults. And also in case if you're doing a fault grading, you just make sure that all the fault that is being, means the test that you run has checks that whether all those faults are being validated. So it just says like 100 faults tests are being run and 100 faults are being detected. Gives you saying that 100 faults coverage is done. But now once the faults are detected and how fast is the recovery is being done, helps you out in fault coverage data and fault grading of your SOC. So there's also one question. How can we learn about emulation and Veloci tool? I would refer to Verification Academy. So that's where you would be able to get all the data. Oh, there's a good lot of questions coming in. Sir, by using high level synthesis, can we use hardware using C, C++, right? So in that approach, where do we use emulation? Is it after RTL generation or before? Yes. So as you know, there was also discussion that you can have high-level synthesis of writing code in C or C++. If you're converting that into an hardware to an RTL, yes, you can use that part of your DUT. If not, if it is part of your test bench, you can communicate your C, C++ with your DUT using SVDPI or DPI, import export calls. Please explain what simulator can do that okay, there's one more question. Please explain what simulator can do that emulator cannot do. Simulator does everything. Emulator does functional verification, but simulation is slow. When the designs or the tests are long, emulator can run faster. And timing analysis, simulation can be done and emulation cannot do timing. Okay, there's one more question. When we are prototyping design on FPGA, then only logic, not other issues like crosstalk on physical layer on ASIC. So do the industry need more advanced prototyping methods? That is true, but physical layer or crosstalk cannot be analyzed on the real hardware platform. On the actual platform has his limitations because of the analog on the timing. But yeah, if you have designed an application-based prototype board, which is ready to be as a part of application, you could use EMCs or something that could help you out to extract the crosstalk interferences. Or the physical layers issues on ASIC, I may not be the right person to answer. Yeah, I think there's a question, is Veloci available in AWS and Azure or GCP? I think on AWS, Amazon Workspace, it should be available, but you need to contact the person to get an access. Yes, there's a question, can we do code and functional coverage in emulation? Yes, you can do code and coverage in an emulation. So emulation verify, there's one more question, emulation verify functional verification, right? Yes. What do you mean by functional verification? Both the same. Yes, functional verification is like, you try to analyze whatever is the code that's written, it is working as expected. Like if you write a code as an AND gate, it should work as an AND gate, or works as a flop, it should be synthesized as a flop and works as a flop as a given clock edge. So that's where we say is a functional verification. We don't bother whether it's coming before or after. We just make sure that the code is written and has right logic and is being. Just jumping up and what about security related issues regarding hardware emulation? Yes, so whatever the code, if it's encrypted, if you're talking about encrypted code, yes, it will be encrypted. It should be encrypted as per IEEE standards. And security issues, in case the design that's there on the hardware, it is all into, a jumbled data, so it cannot be viewed as a text or anything. So you cannot access the hardware at all. Okay, how much time I have? So I'm just pulling out my each has a maximum clock speed while some ASIC. Okay, there's one question which says FPGA has a maximum clock speed for working while some ASIC run on much faster clock, then how such designs are verified? Yes, as maximum clock speeds working on some ASICs. On FPGAs, it runs much faster. Much faster. Then how such designs are verified? It should not be an issue when the clocks are fast, until unless there is no interferences in the design. So I'm just bringing up my, okay, so let me just share my screen quickly if I have few minutes to the demo.
Harish, can you repeat that question on FPGA emulation?
Yes, yes, please.
Yeah. So really how the industry does it is basically there are two ways of looking at it. First thing is they want to make sure that they don't want any logical issues. So they reduce speed operation and do an emulation on the FPGA. That is what is most widely practiced in the industry. But due to advancement of the fabrics in the FPGA today, a lot of logic is able to run at speed, right? So use the FPGA functionality and for all the logic issues. Remember in Mr. Ruchi Dixit said 40% are logical bugs. So at least that much problem is resolved by an FPGA emulation. Over to you, Harish.
Thanks. So I just thought people are asking to show a quick demo. So I'm just running a test here. I'm just also take the same Mandelbrot design. I believe people are able to see. So I'm just running, loading the design on the emulator. I've actually compiled. So this is on the runtime. It's loaded. The design is loaded onto the emulator. It does all the memory initialization and the code. It's as per the memory. And now it's connecting. It started my run. So it started plotting the data. So I need to configure my capture transactor, which actually, so it's plotting the Mandelbrot, the graphics. So I just go here, check the interface, the configuration. So I see that there is an process already running. Enable it, and I just run this. So this is what is happening here. So you see there's a lot of pixels here. So now I can actually even do video statistics. So you can see the, should be a, can just video statistics somewhere. Yeah, this is the only display pixels, the size. So I can actually, this is running on the emulator, but in a simulator, it takes time. It's already plotted. So I'm just trying to, okay. Just need. So as per that equation, there's a lot of iterations and, the design has been plotted with reference to X and Y axis. So now, I can control this, say this is an SOC that is there and then there is a lot of fault or this pixels is there, it's not clear. So I just come here, I've created in such a way that if I press an F, all those pixels, the dots on this picture is being removed. So I disable those faults. So just to give an idea, and I can just do a power, block some of that engine. Let's see. So I'm just switching off some of the block of that particular the equation so that I plot only half of it. So this way, I can switch on and switch off, which will help me in validating the power of the design. So just to give an idea how it is, and then I can actually zoom in. So there is good lot of, but that's a max speed that it can go. Shift plus, so I can just back. I can just use I for iteration. I see the values changing here. So you see the color, so that's the stability. As it goes out of the stability of the equation, the color changes. So this is how the code it looks. So I just quit this just to give you a quick, I'll just take another 2 minutes of time. Just quit here. I have the waveform. I can just put so this is the code. I can just see the code and I have power domains. I'll just pull out, say like X and Y. Expand. There are many equations. So you can actually see this code and then, you can just go and enable your, so you see the values at each and every code and so for example, I just take one of this, say like X position, I just add to the path browser. So these all helps in further debuggability of your design. And, now you can see expand and then actually see somewhere memory is written to this. So this is the memory data. So this is how the GUI looks, but whole of these things is actually running behind on the hardware. And the code is this is an RTL is what I just pulled it into the slides. So you could see the data at that particular time of this particular time, what was the data. So this is how it goes. Since it's a big path, so it is only one remains one big bus. So there's a data just transition happening. So that's why you see X and then others are all doing it. So if you take this particular signal, there's a bus. So bus would be looking at that. X is a bus. Yeah. So this is what I have. I could not show you the compile. Compile would take a few minutes, but I didn't want it to hold the other sessions. So I just stop here. Thanks for all your time, but I just back on to my questions. If there is any questions, I will pick it up. Actually, what is, can we run VIP? Yes, we should be watching verification IP, but if it is synthesizable, it becomes easier. If not, you'll have to remodel some of your BFMs. It is easy to remodel. What is gated clock and its use? So gated clock is like a normal clock generation, but you use a gate to enable when you need the clock. So that's where you have a gated clock is what we call as a gated clock. So it helps you, especially in most of the power analysis. I'm just taking the last question that's coming on the screen, like I've not scrolled up. So if there is any particular question, Firoz, just let me know, I can just answer.
Yes, sir. Sir, I think we are done with the question answer set. Yeah, there is no more new questions, sir.
Okay.
So,
All right. Thanks a lot, everybody, and thanks for your patience. Probably I was faster, so and hope it is helpful.
thank you, sir. Thank you for such a wonderful talk, sir. So with this, I would like to conclude the first half of the session. Uh, we will take a 20 minutes break for lunch, and after 20 minutes, we will be again connecting at 3 p.m. for the next session. Harish sir, thank you on behalf of Dr. Gaurav Trivedi sir. I would like to thank you since he is not here connected right now. But thank you, sir, for your wonderful talk and the time, sir, We are really happy to have you with us, sir. Thank you, sir.
Thank you. Thanks a lot, ma'am. Appreciate all of them for helping me out and answering and
Thank you,
asking
sir.
questions.
Puneet, sir, we will be connecting at 3 p.m. today. Is it okay, sir?
Yeah, perfect.
Okay. So we will break for lunch. So all the participants are requested to please join us at 3 p.m. Thank you. Hello, good afternoon, sir.
Good afternoon.
So can we start?
Yeah, I'm ready. Or basically, maybe some attendees need to come in. I see some people have left and they are joining. So maybe we should give them 5 more minutes and then we start.
Okay, sure, sir, sure. Thank you, sir.
Okay, Firozaji, maybe we can start now.
Good afternoon all. So now we will be starting with the session with Mr. Puneet Goyal sir. In the morning, already Dr. Gaurav Trivedi sir has introduced Mr. Puneet Goyal sir. Sir is working as a Chief Technical Officer in Co-Verify, and he is working in the area of UVM design and VLSI design for the past 15 to 20 years. So with that, I would request Puneet Goyal sir to please start with the session. Thank you, sir.
Okay. Hello, everybody. So I'll be talking about embedded UVM for the next few days. And today we'll start with some introduction. This is the overview of what we'll be doing. Okay, so we will first take a look at SOC design flow because from yesterday, I understand many of you don't have, deep background in VLSI. So to put things in perspective, we'll take a look at how an SOC is designed. Then we'll take a look at hardware design landscape, basically how things are changing and what, brings in FPGAs. FPGAs are becoming more important. So we'll take a look at why and how FPGAs are becoming important. And then later on, we take a look at verification trends and challenges, how verification landscape is changing. And finally, we'll take a look at embedded UVM, a very, very small introduction to embedded UVM and how it can be used for emulation. So we start with SOC design flow. Okay, so like software design flow or like any even if you go for how to design a car, so you will start with very abstract concepts and then you'll keep refining those. The same way when we start designing an SOC or any chip, then we start with functional specifications which are very abstract, and then we keep on refining those. Finally, it leads to the chip. So there are multiple steps involved. Each step refines the output from the previous step. The whole process may take anything between 1 to 3 years or even more. So if it's a very new chip with a lot of IP getting developed, then it takes more time. But in many cases, you just pick a lot of IP from other places and integrate the things together and maybe refine the IPs a little bit. So it may take less time and you may be able to get a chip within a year. So let's see all these steps in detail. The first step is functional specification, which is mostly made by a technical marketing team. This is not the general marketing team. These people are the people who interact with customers. They are technical otherwise, so they are not sales people. They are technical marketing team, and they understand what kind of what kind of specs are needed by the customers, and all those things are collated into a document, and this is often called the requirement document. And this document then leads to the next step, which is the behavioral description. Mostly this step, where we involve MATLAB and other things, this is taken to just to have a kind of feasibility, whether the chip will be feasible and what kind of hardware architecture it would be having. And so all those things are refined. And it's a very, very manual step where somebody will create MATLAB model for the whole system. And that MATLAB model will be used as a reference for later steps. This MATLAB model is not going to be timing accurate, but it will give you a rough idea of how the system is going to behave. In many cases, when you, and this is evolving flow, so when you need to have a better handle at timing and performance of the chip, then instead of MATLAB, you can also use System C along with platforms from various EDA vendors, like you have Virtualizer from Synopsys and Vista from Mentor Graphics. So these are popular virtual platforms, and these can be used for modeling the whole system in System C and C++. And then these platforms can also be used parallelly for software development. And then after this step, you refine the whole thing further. Whether you have MATLAB models or you have System C models, you refine them into RTL, which is Register Transfer Language. And this can be either Verilog or it can be VHDL. And this is going to be the most defining moment of the hardware design. So RTL is the most prominent of all the abstraction levels in multiple ways. RTL is implementation agnostic, meaning thereby if you have RTL, you can take the RTL to FPGA, to ASIC, various foundries of the ASIC, or you may even take it to FPGA prototyping or a Veloce kind of emulation platform. So RTL is the complete functional description of the chip. And it will be cycle accurate, it will be timing accurate in that sense. All the steps beyond RTL abstraction are implementation dependent and highly automated. So most of the manual intervention stops here. After this, you are going to take it to tools. You are going to give timing specifications, and you are going to synthesize and whatever place and route and other things which we are going to see now. But all those things are mostly specification rather than refinement of model. So then at gate netlist level, where you are synthesizing the RTL, so there'll be multiple steps. There'll be DFT, there'll be MBIST, and the final netlist is going to be purely a structural Verilog model. So whether you have written RTL in VHDL or in Verilog, at gate level, it's kind of a standard to have the gate level netlist in Verilog, and you won't be using VHDL after this. And finally, it's gate level simulations are often an important criteria for tape-out. Though static analysis and static formal verification tools are available to make sure that the gate level matches RTL, but still it's in most cases people will be running gate level simulations before they tape out. So you won't be running all the simulations at gate level, but you will be running some 4 or 5 test cases which are kind of making sure that the gate level netlist works. Okay. And finally, physical design, which is very elaborate. There'll be multiple steps. This flow itself will take anything between 3 to 6 months to complete. And but we won't be talking much about it. As Ruchir had suggested earlier in the day, most of after what you do at gate level and beyond, it's a lot of repetitive work. So this is where I believe a lot of machine learning and artificial intelligence is going to come in later in the coming time. Okay. So this is the flow diagram. In slightly more details, you have the specifications. There'll be a team who will decide what part to do in hardware and what part to do in software. And we talk about software here because we are talking about system on chip, which will certainly have a processor sitting there. In most cases, you have multiple processors on a single chip these days. So all that kind of partition will be done. So there'll be an architecture team who will take a call what kind of processor you will be having, how many cores, and whether some of the processors are going to be real time or they are going to be normal processors. All those calls will be made. And then you will have a lot of generic IPs. I'll explain all this in a little bit detail in the next few slides. And a lot of work will be there on SOC integration, that is putting together all the IPs along with your customer hardware IP. This is what actually you are trying to create. The other IPs you are trying to buy from other vendors. Like for example, if you are creating a chip for network routing, then Ethernet module, etc., you buy from vendors, and unless you are a very big company and you also have an Ethernet module. But in most cases, you'll buy it from different vendors, and the actual routing algorithm will be your intellectual property. So that's what you do yourself, and then you integrate everything, go through the functional simulations, and then through prototyping or emulation, either of those, and then finally the physical design. There's also software development which is happening parallelly, and that parallel development will be done through virtual platforms, which might be TLM based, like System C based, or there might be QEMU based, which is also a popular platform for software development. So QEMU is a software emulator wherein you can create models of hardware, and it's more software oriented than a System C based virtual platform would be. So the difference here is going to be, System C based models are going to be timing accurate, while QEMU kind of stuff will be completely, it won't have a sense of time. And what happens is, if you are, for example, creating a cell phone, and then you have to take a call whether your cell phone is going to have a processor which runs at 1.6 gigahertz clock or at 1.8 gigahertz clock, then you probably want to do that kind of analysis in System C, because if you go with a slower processor, probably you are saving on power, so your battery is going to run longer, and but your cell phone is not going to be as responsive. If you go for higher frequency, then it's going to take more power, it's going to be more responsive, but there has to be some matching. Like if your processor is high speed, but your other peripherals in your RF system and the kind of flash memory you are integrating, or if all those things are not matching, then probably you don't want a high frequency processor. So all that kind of decisions can be taken only with a virtual platform which is timing accurate. So that's the call. Like if you want to do that kind of analysis, but not many companies would do that. So only the big companies like Samsung, Intel, or all these companies will be doing it, but the smaller companies will not be doing this kind of analysis. So that will be the difference between a made in China phone and an Apple phone. So Apple phone will be, all the components will be explored with a virtual platform, and then a matching will be done, and that way they'll evolve the system. Okay. So as we look at this diagram, it's important to understand the top portion of the diagram is called front end. Till we finish the functional simulations, it's called front end. The implementation part is called the back end. So you have design and implementation. Or actually, it's also good to look at it in this way, that in the top portion, you model the design. Therefore, the model gets incrementally refined. In the bottom portion, you make specifications, whether they are timing specifications, or if you are doing place and route, then you specify where different blocks will be, where there'll be how the blocks will be interacting, and where they will be placed on the ASIC or SOC. And then it's also good to look at it from the view of programming and scripting. So if you want to make a career move and you want to know whether you should be doing front end or back end, front end is more programming oriented, back end is more data oriented. So you'll have a lot of data and you'll be automating the flow. In front end, you will be instead of crunching data, you will be creating algorithms and you will be coding those algorithms, whether you do it in hardware or for test benching, but you'll be programming. Okay, then the front end portion is a lot of manual stuff. So when you refine the models or when you create test benches, all this is not much automation can be done there. On the other hand, backend will be highly automated. So you will have, and it will be also very, very dependent on what tools you are using, whether you are using tools from Synopsys, Cadence, or Mentor, or maybe Magma. So depending on what kind of tools you use, your whole flow will be automated depending on the tools you use. On the other hand, the front end portion is slightly more agnostic of the tools you use. So you will be using an editor to create Verilog or VHDL files, or similarly the test bench and system Verilog, but it will be a manual process. Simulation is done in a tool, but simulation will only take in your manually created design or test bench. So it doesn't depend so much on the tool. The backend process is completely tool oriented. Backend process is formal and static in nature. So you can take, for example, gate level netlist, and you can compare it with DFT netlist. So after gate level, you insert DFT, that is designed for testability, and you also insert membist, memory bist, which is for memory debuggability after the chip comes out. So all those things are done by various tools, and when you want to know whether your DFT process has been completed without any problem, then you run a formal verification tool, and that tool will tell you whether the gate netlist match or not. Okay, so formal and static means something where you don't really add much input. You are running those tools, and then a lot of debugging will happen. While functional means you will be doing a lot of functional specification of the design, and thereby you will be running a functional simulation. So functional simulation means you will be really finding out whether the design works as per the specifications or not. So there is one part of formal verification which is slightly, I put that in dash, and this part is assertion specific. So you want to find out whether the assertions hold or not. So that is, really, there you need to apply your logic. So you need to make sure whether the assertions are, so how to make sure that the assertions are getting met or not. So all that needs to be coded, and yeah, so but most of the times it's a functional simulation where you will be coding and you will be putting in algorithms. So in this workshop, we won't be talking about formal. We'll be focusing on functional verification and emulation. So the portions that we'll be focusing on are highlighted in yellow. We will not be doing any board level stuff, but board level stuff is also, a lot of tests that you run that you write for functional verification can be run at board level, so that way it is related, but we won't be doing that. So we won't touch board level validation. We will only talk about functional simulation and emulation. So before that, some latest developments in hardware. So I want to touch base on that, and basically I'll also talk about FPGAs and how FPGAs are becoming more important as we go. So we start with Moore's law, and multiple aspects of Moore's law. One aspect which is basically the Moore's law, the growing complexity, the transistor count of a chip. Okay, so we'll focus on this aspect first. Then later on, we'll also talk about the CPU performance. If your chip is basically a processor, then how the clock frequencies are evolving as we go. And that also is true for other chips, which may not be processor centric, which may be data path centric, but the clock frequencies are stagnating. So we'll talk about that aspect later. First, let us focus on the main Moore's law. That means we focus on number of transistors in a dense integrated circuit. So Moore's law is an observation which says in a dense integrated circuit, the number of transistors doubles every 2 years. And then there is a corollary, which basically, there are many corollaries, but this one is important. Compute performance doubles every year and a half. So after every 18 months, you get a processor which works twice as fast as a previous processor. So unfortunately, this no longer holds true since 2005, and we'll talk about it later. So now focusing on growing number of transistors. So we have Moore's law, that means the number of transistors. So the number of transistors double every 2 years. That means every year, the number of transistors are growing by 40%. Okay. Now, given the tool set, given our engineers, given the skill of an engineer cannot, keep on evolving at that faster rate that he is able to handle 40% more transistors in the next year. Okay. So the design productivity is an average engineer, how much he can handle. So the design productivity is increasing because the skill is increasing. The tools that a design engineer uses, the methodology he uses, all that is evolving, and that's how design productivity is increasing. We'll talk about some of that stuff later. But right now, this slide notes, the design productivity increases by an average of 20% a year. So this gap that is therefore produced between design productivity and the technical, feasibility in a chip, you can have much more in a chip. So this is called design gap. And this design gap, how do you fill this design gap? You need to put more and more design engineers, more and more resources, and that's how. So the team size is going to grow, and that's how the design gap will be filled. And then there's a verification gap, which means that verification engineers, how much they can handle given the way the tools are getting better and the way the methodology is evolving. So there is also a gap between design productivity and verification productivity. And therefore, the number of verification resources, which means engineers as well as machines running verification, that is growing exponentially. So Ruchir, in the talk he gave in the morning, he told about that figure, that it's increasing by 10.4% every year compounded. So typically after 6 years, you'll have twice as many verification engineers as you had earlier, and probably twice as many machines running verification simulations. Okay. So factors that are aiding design productivity, meaning thereby design is going to evolve faster and design is evolving faster because of these factors. One is what happened in 1980s. Before 1980s, people used to have paper graphs, and on paper graphs they'll draw different polygons, and that kind of graph will be used to manufacture an IC. So in 1980s, EDA came into being. So roughly 1980s, EDA became mainstream. So you'll have schematics, and you'll have layouts and spice simulation. So this added to design productivity. Had this not happened, probably the designs, the ICs would have been very primitive, and we wouldn't have seen Moore's law getting applied, because the technology wouldn't have developed at that rate. Then in 1990s, we had automatic RTL synthesis, place and route RTL simulation, compared to custom layout. So it's important to understand. 1980, what happened was EDA, which was that basic EDA where you will take help of a computer to draw schematic, to make layout, and that layout will be used for fabrication of the chip. And you'll also have spice simulations, so that you can make more complicated chips. Now, this step in 1990s, the automatic RTL synthesis. So this was a big leap, and actually this is the biggest leap in SoC design. So with this, you are able to have literally hundreds and billions of gates in a design today. And but what happens is, if you compare schematic with RTL, when you do RTL, you do a lot of automation, and there is a penalty of about 2x. Like if you were not to make a design in RTL, and if you were to do schematic and layout level stuff manually, then you probably can create a chip which runs 2 times faster and is taking area which is less, which is 50% less. But then you can't make very big chips. But if you do RTL synthesis and take this flow, then you have a penalty, but you can create big chips. Okay. Now, there are areas where RTL either doesn't help, or people don't do it because they really want very fast chips. So one area is analog, where RTL doesn't help. The other area is the core part of the processor. Like you have processors from Intel and AMD. So the core part of processor, which really runs at 4 gigahertz and above, that will be done manually. So that will be done, that design will be done at CMOS level, transistor level manually. Okay. So a large percentage of digital designs will be synthesized, and that's how we see a lot of design productivity. In 2000 and later, we saw something called design IP reuse. We are going to talk about it later as well. And 2010 onwards, we have behavioral synthesis as well as FPGA. We will see how that is evolving. So this is the typical SoC. As you can see, most of the SoC is the processor, the subsystem of the processor. Remember, this may not be a single core processor. There may be multiple processors, multi-core processors, as well as there could be multiple processor systems. Each system will have multiple cores, and there'll be multiple processor systems. Maybe one of them is for control path, the other one is for data path, or there might be multiple data paths. And for example, in a mobile phone, there is a separate processor system for user interface, which needs to be very fast, and there is a separate one for the RF. Okay, so that's how an SoC will be. So typically 50% of it will be processor system and the related stuff, the memory controllers and the parts which are very closely related to the processor. And then another 20% or so will be generic peripherals. Those are for communication between different chips. So it can be Ethernet MAC or UART, SPI, the popular peripheral devices. So all of them will be there. And then a small portion, depending on what kind of chip you are making, this portion may be taking a lot of area, but usually it takes a fraction of the chip, will be your custom logic. Okay, so a large percent of the chip will be generic, will be reusable across various chips. And typically the design team will go shopping and buy these modules, the processor. So there'll be very few design teams who will be creating their own processors. So the processor will be bought from one company. For example, if you are creating a mobile phone, then probably you'll buy the processor from ARM. you'll license the processor from ARM, and then you'll use it just as you get it. And the other peripherals as well, for example, the Ethernet MAC, the ADC, USB, all these also, there are various vendors who basically create a library of these peripherals and then license each of these peripherals as per your need to you. Okay. So that's how SOCs are made. A lot of it is repetitive, and that's what started happening in year 2000. Before 2000, SOCs were not so complex, and people used to make their own design, completely their own design, because typically SOC as it is started after 2000. Before that, it didn't used to be system on chip. It used to be some particular module um, in a chip. So it would be probably, for example, it would be just the data path of the network router in a chip that way. But since 2000, SOC, that means system on chip, which will have processor and other peripherals within the same chip. It's a complete system. So that movement started only 2000 onwards. And that's when you started seeing a lot of design IP reuse. Okay, now it's important to note that these modules like the Ethernet MAC and even the processor and memory controllers, etc., they will need customization. For example, how much cache you are going to use in your SOC and how many levels of cache you are going to have. Similarly, what kind of flash you are using, what kind of SRAM is there, whether there is whether you're using some off-chip memory like DDR, and whether it's DDR3, DDR4, all those will be specifications of the chip. Similarly, for Ethernet, you will have not only you will have whether it's gigabit Ethernet or 10G Ethernet, you'll also have, even after you decide that it's going to be 10G Ethernet, there'll be various parameters. For example, there'll be some sort of buffering inside Ethernet. When it receives data, it keeps it in a buffer. So how big the buffer is going to be, how the Ethernet MAC is going to interact with the chip, with the processor, whether it's APB bus, AXI bus, or some other interface. So all those things are customizable. Okay. Now, why I'm talking about this is because when a design is provided to SOC team by a vendor, so the vendor will be customizing the design as per the need of the SOC. Basically, that team is the customer. So the SOC designer will specify, I need this kind of Ethernet, and so this kind of customization will be done. In a lot of cases, the customization will be done through some scripting. When you make Ethernet MAC IP, if I'm a vendor and I'm making it, then instead of just writing RTL, I'll basically write an RTL generator. So it will be a program which will create that IP once I give the parameters to the program. Okay, so say it's a Perl script which writes out very long, and this Perl script takes some arguments where I specify what kind of Ethernet interface will be there on the external side, whether it's going to be GMII or it's going to be some other interface. And similarly, what kind of interface will be there with the processor, and similarly the other aspects of the MAC. Okay, so so my Perl script will take these parameters and generate that RTL for me, and then before delivering that RTL to the SOC team, the people who are making the chip, I will run basic verification on this design and then pass it over. Okay. This typically affects the way you do verification because you have taken IPs from various vendors. So one thing is, when you take an IP from a vendor, you also take a verification test bench for that IP. Okay, so this is the handoff flow on the top right. If you are a hardware IP developer and you are giving the design IP to the SOC integration team, in addition to the design IP, you will also provide the verification IP. We'll talk about it in slightly more details later. So IP development team extensively tests the design IP using UVM VIP in most cases today because UVM adoption is increasing, and UVM provides a lot of test bench infrastructure, a lot of constructs which help creating a test bench, and UVM is also a standard, IEEE standard. So it's the wide adoption part which is more important, because if I'm using, the hardware developer could be sitting in a different company and he may be selling the IP to the SOC integrator. So if they are in two different companies, they may not have same development flow. So that's why the standard becomes important. If he adheres to UVM and the SOC integrator also adheres to UVM, that will mean that the VIP, the verification IP provided by the developer to the SOC integrator will be reusable. Okay, so this is how it happens. The IP development team hands over the IP, which is going to be RTL, to the SOC integration team. The SOC integration team uses the UVM methodology. So they also have to be using UVM. Both of them have to be UVM for reuse to happen. And then the IP level test bench. So basically that's the test bench this guy created for IP level verification. It directly integrates into the system level test bench through the verification IP. So this is how reuse happens in verification test benches as well. So this kind of reuse helps reduce verification gap, because when one case would happen if there was no UVM or any standard methodology, then the SOC integrator will have to create the whole test bench himself, because he is having a different methodology, because he's working for a different company and there's no standard. So in that case, he'll have some ad hoc methodology wherein if say he's using C++ based verification or C based verification, so this guy will not be able to help him. So he may have done a verification using Verilog, and this guy adheres to a methodology which doesn't use Verilog, or even if it uses Verilog, the test bench is written in a way that the verification IP that this guy creates will not be integrable. So that's why, a methodology is very important, and a universal methodology in that sense, because if it's same everywhere, then only reuse can happen. So now we come to FPGAs, and we try to take a look whether FPGAs can help reduce design gap or verification gap. So as we saw earlier, synthesis helped reduce a lot of design gap. But or in case of FPGAs, though productivity-wise, FPGAs are very strong, meaning thereby, if you are creating an ASIC and you take, say, 3 months to do your front end, then later on, it will take you 6 months to do back end, and then another 3 months for fabrication of the chip. In case of FPGAs, after taking 3 months for front end development, it will typically be, sometimes just 1 day or sometimes a week to map that design to an FPGA. So that way, it helps you with design gap, because the design productivity increases, right? So therefore, the gap will reduce. But the problem with FPGAs is that a typical design, if you do it in ASIC, then it's going to be very efficient in area, it's going to be efficient in power, and it's going to be very fast. In a typical FPGA, it's going to take 40 times more, silicon resources. It may generate as much as 10% more power. Power means it's the heat that is getting generated, and it may be slower by a factor of 10. See, FPGAs are also evolving, so these figures which I've taken from the web, they may be slightly outdated, but these are the ballpark figures for a typical FPGA. Okay, so just an analogy to understand things. If we compare different stuff in software and hardware, if transistor level design, that's the CMOS design which used to happen in 1980s. Okay, so if we take an analogy of transistor level design, then it's analogous to assembly language. If you want to write the most efficient code, then you do it in assembly language, but you can't scale up. You can't write a lot of code. Similarly, if you do design in CMOS, it will be the most efficient design in terms of area and power, but you will not be able to scale up. Okay, you won't be able to create, for example, a billion gate design. Similarly, if you are doing RTL level design, then that is comparable with system programming languages like C, C++. Almost as fast as assembly language, okay, maybe 90% as fast, but yet not the fastest. Similarly, RTL design is not going to be the fastest, but it will help you scale up. The same way C or C++ can be used for writing very big software systems. Okay, then FPGA, it can be compared to scripting languages like Python and Ruby. Very efficient, very productive. So you can, if you are doing something in C++, you have to take care of memory allocation, deallocation, and a lot of stuff. Python can do it for you. So it's very productive. You can write a program in Python in a few hours, which would have taken you days to write in C or C++. Same way, if you are using FPGAs, you can be very productive. You can write, you can design hardware within days, and you can map it to FPGA and get it working. But then it's not going to be as efficient as RTL-based synthesized designs, which get mapped to, see, RTL-based designs can get mapped to FPGA, but if you map it to ASIC, it's going to be a much more efficient. Okay. Now here is, so SOC FPGA is where we get best of the two worlds. So now I've taken the same diagram which I took for explaining what an SOC is, because you know, I took this for how IP reuse helps with increasing my productivity. So it's the same diagram. Now the idea is most of the modules in this diagram are reuse modules. So they are kind of generic modules. So anytime you design an SOC, you will need a processor, you will need a memory controller, you will need Ethernet, various interface modules, etc. So what SOC FPGA does is it creates, so SOC FPGA will have all the generic modules, including the processor and the peripherals, and then it will give you a programmable, you know, core, which is FPGA, which is tightly integrated with the processor, and therefore the interface between the processor and the programmable core is very fast. Now the idea is that you are not doing the whole chip in FPGA, you are just doing the customizable part of the chip in FPGA. So you don't lose a lot on area, and you don't lose a lot on power, because the power of the processor, the power taken by the processor and the other peripherals is optimized. Only a custom logic is taking more power. Okay, so SOC FPGA helps fill a lot of productivity, a lot of design gap in that way, because we just need to program our custom logic into the FPGA cores, and we get the whole design done. All right. So now still there'll be questions about how about, if I needed a different set of processors, like how about if I needed a quad core processor instead of single core processor. So SOC FPGAs will be available in various flavors. So I'll need to choose. I choose a high-end SOC FPGA or I choose a low-end processor with SOC FPGA. So there'll be different flavors available. Okay, now there is a chance nothing suits my specification and I'm out of luck, but there's a good chance that I get a SOC FPGA which matches my specification. Okay, now not that every SOC will be replaced by SOC FPGA, but one factor which is going to be important, and that's how things are moving, that's how things are evolving in the world. If you need, say for example, more than a million chips after you design the SOC, and you think you need a more than million physical chips with you, then you probably want to make an ASIC. But how the things are evolving in future, there are a lot of designs which don't need a million chips. They just need, say, 10,000 chips. So all those designs will make use of SOC FPGA. And that's the trend. Like a lot of designs in future, and currently a lot of people want to create designs which are highly customized, and therefore because they are highly customized, there are not a lot of users. There are very, very specific users or use cases, I should say, for those designs. Okay, now figure this. This snapshot I've taken from Twitter. This was a tweet by Joe Armstrong, who is a domain expert in hardware and software. So it's very interesting. Once upon a time, my boss asked me to study if we should use C++ or Erlang for a specialist XML parser to be used in a product for reasons of speed and not energy. My recommendation was FPGA. Okay, so this is where this hardware software partition is coming into picture. So people who are really into speed, they are using processors. They are using FPGAs. Now this is a very it's kind of very surprising. I mean, I would say 90% of the designers will be surprised that somebody made XML parser, which is typically a software job. They made it in FPGA. Okay, and the relative speed of C++ Erlang was irrelevant. So I haven't put all the tweets here. Basically, the design that they made in FPGA ran 3,000 times faster than any software could be made for that XML parser. Just for a background, XML is typically used for transferring data between different tools. So probably this kind of application would be getting a stream of XML data which needed to be parsed very fast, and they used an FPGA for that. Okay, now this I have taken from the SOC design flow. So first of all, the backend part will not be there, because as soon as you synthesize and you place and route on the FPGA, you are done. There is no so place and route of FPGA is, instead of taking 3 months, it will take a day. So there is no elaborate flow here. Now the other parts are, if you are using SOC FPGA, then the left portion of the whole flow will go, because you already have this kind of SOC FPGA, so the rest of the system is already there. Okay, and the right portion of the flow also goes, because FPGA development is so fast that you will take days instead of taking months. So you can start the software driver and other process after you make the FPGA. So the flow becomes very simple. You have the specs, you do the hardware software partition. So you decided you will create an FPGA on SOC FPGA. create the custom hardware IP, do the functional simulation, and generate the SOC bit file. None of this, so custom hardware IP development will take a few days, depending on what you are doing, but the other portions are not going to take a lot of time. Like typically for this kind of XML parser, the bit file generation that includes FPGA place and route and synthesis would not have would not have taken more than a day. Okay, so this is the kind of productivity SOC FPGAs are enabling, and this is a real example. This is a 1-year-old tweet from a domain expert. Now, when we looked at Moore's law, I said we'll be going back to Moore's law and we'll be taking a look at the performance aspect, the corollary of Moore's law, which talks about processor performance. Okay, so since 2005, if you see this graph, the CPU frequency. So in 2005, if you go to your local computer market, then you will find the best computers available, the best desktop computer available in 2005 would be running at 3 gigahertz or 3.5 gigahertz. Is kind of the same today. It may have improved from 3.5 gigahertz to 4 gigahertz, but that's the only improvement. Now, the CPU performance, the architecture evolution also has stagnated. You have kind of done most of the tricks you could do. For example, out of order, execution of commands, pipelining, and various kind of caches that you could do. So all those things, all the tricks you could play, you have already done. Okay, so it's the frequency which is no longer getting faster. It's a big area of concern. So let's see how. So in 2005, and it has to be 2005 because that's when the frequency started stagnating. So Herb Sutter, who is the chief technologist in Microsoft, who looks after development of the Visual C++ compiler. So he wrote a seminal paper titled "The Free Lunch is Over." Okay, so let's understand what this free lunch is about. So till 2005, a lot of you probably were very young when this event occurred. Till 2005, every 2 years, you'll get a processor which runs twice as fast as the previous processor. So the software companies like Microsoft, who Microsoft, everybody knows they are good at making operating systems. So they won't have to work very hard. So they'll release another version of Microsoft Windows every 2 years, and they'll do some changes in the user interface, make some things better in terms of user experience, but they don't have to do anything for increasing the speed of software. Okay, so that's free lunch. You don't have to do anything because after 2 years, the customer probably has a faster CPU. But that's not happening since year 2005. So what is happening is, instead of giving you a processor which is faster, the processor companies are giving you processors which are multi-core. Okay, and you really have to work hard to use multiple cores. You have to, there's a paradigm shift in programming as well, that if you want to create a multi-core enabled software, then multi-core kind of adds a dimension to software development, and software development becomes much more difficult. The other part is, even if you create a multi-core enabled software, so say instead of 1 core, if you are using 4 cores, chances are you are not going to get a performance gain of 4 times, which you expect with 4 cores. Chances are that your software application is going to run only 3 times, or maybe in some cases it's going to run only 1.5 times faster. Okay, so had the frequency kept on increasing, instead of we having to go for multi-core, then things would have been different. With frequency getting double, you get a software which runs at double the speed. Now, to understand all this, we really need to see that at 4 gigahertz, light travels only 7 centimeters. So I've just put it, as a reckoning, as a matter of reckoning, that we are hitting the physical limits of this universe. So 7 centimeters is probably the size of the chip. Not to say that a signal has to travel that much because there'll be aspects of capacitance of various inductance and capacitance effects will be there. So you hit all those limits, and therefore 4 gigahertz is kind of a physical limitation. When you basically what happens is, as you keep increasing frequency of chips, then the power keeps increasing. So at 4 gigahertz, they found that if you keep increasing it beyond 4 gigahertz, then power becomes really, really bad to handle. As a data point, I can tell you that if you take one of the latest processor chips, then the amount of heat it is emitting per unit area, that wafer of silicon, the amount of heat it is emitting per unit area is equal to the amount of heat that is emitted by a coil heater that you use at homes during winter days. Okay, so that's the situation of power. So they clearly couldn't go beyond that, and therefore 4 gigahertz has become a defining frequency of the processors. Now, as we go multi-core way, what people are realizing is that when we go multi-core, since instead of 1 core, we have to, today you have processors which are 32 cores. You have a night landing processor from Intel which has 72 cores, and each core is able to run 4 parallel threads. So that means you have 288 parallel threads running. So when you do parallelization and concurrency at that level, then because all those 72 cores are sitting on the same silicon wafer, so you can't have all of them emitting a lot of heat. So if you look at this graph, and if you look at CPU clock frequency, with multi-core, though the number of cores is increasing, the CPU frequency is going down. And there's an expectation that it will stabilize at around 1 gigahertz instead of 4 gigahertz. Okay, and they also found that if you want to do a lot of cores on the same chip, then it's better to do simpler cores rather than cores which are more complex. So you can't, actually this graph is also going down, the performance per clock graph. So the idea is to create chips which have really hundreds of cores, but those cores are simpler architectures, and those cores are running at slower clock speed. So that's the direction things are moving in. But as Ruchir also talked about data, so that's the problem. That's becoming a lot of problem with processors. So imagine we had gigabit Ethernet. If we see here, so gigabit Ethernet came around year 2002, and no, actually it happened in 2000. So this is about standards. So gigabit Ethernet standard got developed in year 2000. Availability could be a little later. Today there is a standard of 1000 gigabit Ethernet. Okay, now if that's the amount of data which Ethernet is carrying, then who will crunch this data? Who will process this data? The CPU is stuck at 4 gigahertz, the bandwidth of the Ethernet as well as bandwidth of the USB, PCI, everything is increasing. Okay, so here is the trend. In the past, we have seen variations in networking and compute performance. So you will have Ethernet sometimes, when in the past till year 2005, when you get a new standard of Ethernet, so probably because it's a new standard, chances would be you still don't have processor which can process that much data. Okay, but 2 years later, probably processor would be released which can process that much data, and so things were like in a pendulum. Sometimes you have standards which are future looking, and sometimes you will have new processor coming out which will be able to meet the requirements of the standards. But since 2005, processor frequency hasn't increased. So this pendulum has gone. So now the computation is not strong. It's communication which is strong. So it has gone all the way up the roof. It has broken the roof. Okay, so that has repercussions. So one is we have to go multi-core way, but even multi-core is not helping, because multi-core can help with throughput of a system, but it can't help with latency. When you need really fast results, you need low latency, then multi-core, because multi-core will help if you split your data into multiple streams, and then those multiple core server farm probably, or maybe one big system with multi-core CPU is processing your data, and then finally you need to converge also. The results have to come into one place. A typical application, so to say, could be you are getting a lot of data from stock exchanges around the world, and you want to crunch all that data, and you want to make a decision which stock to buy and which stock to sell. Okay, so then all that data that has been crunched has to converge back to one place, and then only we'll have a result. So this will take time. First of all, who will split data into multiple streams? So all that has to be done. It can't be done by a processor. It has to be done in hardware. So what's happening is, if you talk in terms of OSI layers, the international standard, so earlier you had the physical layer and data link layer. They used to get done in, physical layer is really the transmission line, whether it's copper, fiber, or whatever. And data link layer was your Ethernet MAC. So these two layers used to get done in hardware. The upper layers were all getting done in software, because a processor was able to process the data which is coming in. Going forward, and actually currently as well, you can't handle that much data with a network processor or with a host processor as well. So a lot of data crunching, if it has to be done in real time, has to be done by hardware. So hardware and software, they have to work together now. Okay, and this is big. Why it is big? Because if you look at up to networking layer, then this is media layers. Media layer means these network processors are the backbone of internet. So these processors, if you want to do some of them and some part of it in hardware, then you will make a chip and ASIC which will have a processor. And earlier this used to be completely done in software, so there was no domain specific hardware here. Now you have processor. Along with that, a lot of hardware which can be which can crunch IP level data, and therefore the routing can happen. So you make an ASIC out of it. But all the host layers, host means the laptop I'm using, the desktop I'm using, these are the hosts, or the desktop or the servers which are lying at data centers over the cloud. So those are hosts. So these always used to be generic Intel or AMD CPUs. So they didn't have any hardware processor sitting there or any domain-specific hardware sitting there. So Ruche talked about a lot of ASICs getting into data centers. Along with that, what is happening is because the application which needs to be run, for example, if my laptop needs to make things faster, then it cannot be an application-specific IC, because application-specific IC means the application is known. It's my desktop, and nobody knows whether I'm going to run, what kind of application I'm going to run. So it has to be programmable hardware, and that's where FPGAs come in. Okay, so figure this out. Basically, Intel, after acquiring Altera, is making server and even in future maybe desktop and ICs. Right now, it's server and ICs only, which are having big FPGA cores available. Okay, so this is what the future holds. Today, when we run an application in Windows or Linux, the application asks the kernel for DLLs, dynamic libraries, or in Linux, these are shared object files, .so files. With programmable hardware becoming mainstream, applications in future will also request FPGA resources. So you'll have things like you are using Microsoft Excel, and then you invoke a AI algorithm on data that you have in your Excel sheet. And if somebody has coded that AI algorithm in software, maybe it's taking too much time, too much runtime, and you don't want to have that kind of lag while processing your Excel data. So it may as well be that when you invoke a formula, it actually gets processed by the FPGA. So this is what is happening. This is what the future holds. The Linux kernel already has a FPGA manager. So basically, memory manager is when an application loads, the only hardware resource today an application asks the kernel for is memory. So there are applications which will also ask for peripherals like USB, etc. But I'm not talking about those. A generic application, software application, will only ask for memory, and the kernel will provide, will either say I don't have memory, so it will refuse to provide, or it will provide memory to the application. In future, you're also going to see FPGA manager. It's already a reality. So an application can ask for FPGA resources from the kernel, and the kernel, if that resource is available, will provide that resource to the application. Now, this is slightly different from what we have been discussing. This is another trend in hardware, that's the open source hardware. So most of us would be aware of RISC-V, which is an open source processor core developed by Berkeley. So we are witnessing how RISC-V has created an ecosystem for open source in the hardware domain. FPGA-based programmable hardware will take it to the next level. How? Just imagine this. Today, open source is the main driver of software in the world. Okay, if you talk about C compiler, probably you are talking about GCC, which is open source. If you are talking about different web servers in the world, they are all running Linux, which is again open source. Now, just as an example, say as Intel is projecting, say the data centers start getting a large number of data centers. So it will happen ultimately, may take 2 years or 5 years, but a large percentage of data center servers will have FPGA resources available. Now, Apache and Nginx, these are the two most popular server and web server engines. So, when you go to a website, then that website will be So there'll be an application responding to your request when you go to a website. So the web server will be responding to you. So these are the two most popular web server daemons that people are using. One is Nginx, the other is Apache. Both are open source. And in future, if open source, if FPGA resources are available on the processor, such applications for their encryption, decryption, and other needs, they are going to utilize FPGA resources. So if open source software starts creating open source hardware, starts using hardware, it's going to be open source hardware. And this is going to be big. Today when we talk about ASICs or even about FPGAs, then we are talking about, if you take how many FPGA engineers will be there in the world, it won't be in millions, it will be much less. ASIC will be, maybe they are in a million range. But when you talk about software, it's much, much more. And all these FPGA enabled processor cores will be available to all the software engineers. And therefore, the RTL kind of design capabilities will be useful at a much larger scale. Okay, so imagine any Android application which is using some kind of processing at the hub. It may be a game, it may be your traffic navigator. Then if you have FPGAs available, your application will become much faster, as we saw in that example of XML parsing, which became faster by a factor of 3,000 as soon as they started using FPGA instead of C or C++. So we expect a lot of open source hardware to become reality in future. Now, a brief look at verification trends. One verification trend is because of a lot of hardware and software interaction that is already happening. So when that guy Joe, he talks about XML parser, then that XML parser will be fast only if it's tightly integrated with software. So it will be fast only if the FPGA is lying right next to the processor. So my guess is, though he didn't give the details, but my guess is he used some kind of SOC FPGA. In an SOC FPGA, your software interacts with the hardware at a very, the layer, which the interaction layer is very thin. Okay, so it's a very tight bonding between hardware and software. And you'll have things like software sending data to hardware and getting back data from hardware. And after doing some other software processing, again, sending the same data after some processing to hardware. So it can be a zigzag kind of stuff. So the key point is you use hardware where you basically have a software bottleneck where you have a lot of performance getting a performance issue with software. So at that point you want to use hardware. So it can a real project, a software project could be doing a lot of zigzag with hardware in future. So the challenge is, how do you verify hardware and software together? Okay. The other challenge is that you are doing what software was doing 5 years back. So, earlier it was kind of whatever needs more efficiency, and those would be simple things, you use hardware there. Now the thing is, hardware is doing stuff which was getting done by software 5 years back. And software tends to be much more complex than hardware in terms of algorithms. So therefore today, people are doing RTL, which is implementing artificial intelligence algorithms and other stuff. And this is really, really complex. So this becomes a challenge for verification as well. So one challenge is hardware-software co-verification. The other is the complexity of the algorithms that need to be verified. The other challenge lies again in the Moore's law because of this 2005 stuff. So let's understand this. Earlier, until 2005 happened. So every 2 years, there'll be a new project in a big organization. So you tape out a project and you start working on the next project. And the next project will be a bigger chip because of Moore's law, because more transistors are available and you want to do a more complex chip. And but what was helping was the servers you run simulation on, those servers were also getting faster. Okay, so since 2005, there is a break, and your simulation speed has stagnated while the design complexity keeps increasing. Okay, so this 2005 break in the CPU frequency affected verification in a very bad way. So the verification gap started increasing. Okay, so now when the speed got stagnated, the CPU companies started making multi-core processors. But unfortunately, the RTL simulation engines couldn't take advantage of that. It's only recently that you have started seeing multi-core enabled RTL simulations. But still there is a challenge. The challenge is the simulation of the RTL. They are able to take advantage of multi-core, but not the test bench. So there's a difference between how RTL is simulated and how test bench is simulated. Test bench is completely a dynamic code. Okay, a test bench is behavioral. RTL is formal, it's static. So RTL simulation, making it multi-core, is a very different concept than making the test bench multi-core. So the test bench speed is not getting helped by multi-core processors. And test bench has started becoming a bottleneck in verification these days. Then the trend is OpenRISC, the RISC-V processor, which is open source. And there is a challenge. If you look at how open source projects are developed, the developers are sitting across the world. So, there'll be a developer sitting in Berkeley University. There'll be another developer maybe sitting in IIT Madras. Okay, so they have to collaborate, and they have to collaborate using the cloud platforms where the software is, the designed RTL or the designed open source hardware is being kept. So probably RISC-V, for example, is kept on GitHub. Now there is a developer, he wants to make a change, he wants to add a feature or fix a bug into RISC-V code. So he'll pull out from the GitHub, make the changes he wants to make, and put it in again. Okay. Now this is where open source verification becomes important. This kind of scenario cannot be handled by closed source tools. Now, in case he needs to make this is called pull request. He basically clones the GitHub repository at his end, the developer. I'm talking about the developer perspective. He, gets the data, gets the whole design from GitHub by cloning the GitHub repository. Then he makes changes. Then he runs some kind of simulation. Now, see, if it's not open source verification that he's doing, then he's using some proprietary tool to simulate. Okay, now when he simulates, chances are that the other developers who are into this project, they are using a different simulation tool. So he may not see a bug that other people may see. If you take system Verilog license from one EDA vendor and you take system Verilog license from another EDA vendor, and even if your test bench is exactly same, the randomization engine of the two EDA vendors is going to be different. So the same test case will generate different random stimulus in one EDA tool and different random stimulus in the other EDA tool. So one developer, if he sees a bug in one EDA tool, if he wants to communicate that bug to another developer, then he'll pass on the test case. The other developer runs it in the other simulation tool, and he won't see the failure this guy is seeing because they are different EDA tools. Okay, so one way is that all the developers on a particular open source project, they decide on one particular EDA tool and they all start using that EDA tool, which is not possible. There are going to be hundreds of developers. And there are volunteers who just want to volunteer for a few hours in a week, and telling them that they need a particular EDA tool is kind of, you're basically saying you can't work on this project. So for this kind of scenario, and there is a little bit of detail in this diagram. This is called continuous integration, which is very helpful for open source projects. For continuous integration to happen, it has to be, because continuous integration happens on the cloud, it has to be an open source verification tool. Okay, so the point here is, the point I'm trying to make here is, open source hardware development will, in future, like today also, there is a need for open source verification. In future, that need is going to grow. Then there's a trend. So this diagram explains it. RTL simulation is slow. Test bench is, in most of the cases, not a bottleneck if you are using the test bench to verify RTL. But if you are going for emulation or you're going for virtual platform, then test bench becomes a bottleneck, because only the RTL part gets mapped to virtual platform or to the emulation platform. Okay, the test bench cannot be mapped to the virtual platform. So if today you have RTL, which takes 80% of your simulation time in a simulation, and the test bench takes the rest 20%. When you map your RTL to virtual platform or to the emulation platform, the test bench, which was taking 20% earlier, starts taking it more than 80% now. Okay, so you need to make test benches faster as we move to emulation platforms and virtual platforms. And then if you keep using system Verilog, there is DPI overhead. That's the layer between system Verilog and C++, because all the virtual platforms and emulation platforms are compatible with C and C++. They are not directly compatible with system Verilog. And therefore, to pass a transaction from the test bench to a virtual platform or to the emulation platform, you need to invoke C and C++. That means you invoke the DPI layer, which is another overhead. So here's the challenge. Contemporary verification languages, I'm talking about system Verilog here, were drafted with RTL simulation in mind. Simulator performance becomes a bottleneck when test bench emulation, test benching, emulation, or ESL platforms. ESL is electronic system level. It's another name for virtual platforms. Okay, so if you use system Verilog for creating test benches for virtual platforms or emulation, it becomes a bottleneck. It is also becoming a bottleneck, as I said earlier, because RTL simulation is going into multi-core domain. So you are having simulators which can run this RTL simulation instead of on one core. If it's running on 32 cores and it's getting faster by 16 times on a 32 core processor, then you can see the RTL will be taking much less time and test bench will be taking more time. So we need multi-core test benches as well. So these are the takeaways. As verification domain grows, why it grows? It grows because of Moore's law. It grows because of design productivity and the increasing verification gap. That's a challenge. So it grows wider, more transistors with Moore's law, and it grows deeper because more and more what used to be done in software is getting done in hardware today, and that hardware needs to be verified. So there's more complex algorithm which needs to be verified. So as it grows wider, that means as we go for bigger chips which need to be verified, we need multi-core tools. We need more of emulation. We need more engineers to handle simulation and emulation. We need more hardware to run simulation as well as emulation. As it grows deeper, we need layered test benches because, here as we saw earlier, software used to be layered. These are different layers. Now hardware is also layered. So you have the Ethernet layer, you have the IP layer, TCP layer, and the application specific layers, whatever could be there. And this is more communication centric, but most of other domains are also layered. Like even if you are creating a video game, then there'll be different layers of a video game, different software, kind of software stack of a video game. Okay, so as hardware becomes layered, you need layered test benches, you need smarter tools like UVM, you need smarter engineers who know UVM, you need more software. More software means your test bench is going to be more software oriented because you are actually verifying algorithms now instead of simple data crunching. Okay, these are hardwares which are doing work of a software. So what you are actually verifying is software like complexity. So that's where embedded UVM comes in. It's completely open source. So this is one of the embedded verification, embedded UVM perspective. So when you this diagram we already saw in verification IP reuse. So when a designer passes on design to the SOC integrator, he also passes on verification IP along with it, so that the SOC integrator can make sure that integration of RTL design is proper and all the test cases that were provided by the developer is able to run in the integrated environment. So this is the kind of place where he has taken Ethernet block from one vendor and he's trying to integrate it with AXI fabric maybe, and that AXI fabric is coming from another vendor. There are some chances that the features which are there for AXI, the AXI fabric doesn't support some of the features required by the Ethernet AXI interface that this guy is giving him. So that kind of integration issues can happen, and that's why in spite of verification IPs and all this kind of reuse, verification still remains a very complex task. So, but the key point here is the verification IP along with the test cases, it's a handoff criteria. Meaning thereby, if those test cases can be run in the SOC integration environment, you are reasonably sure that your integration is perfect. Similarly, when a software library developer hands over a software library to system integrator, who is a software system integrator, then she passes on a software test sheet along with it. Now, why does she do that? Because she may be developing on Windows, and this guy may be using the same library in Android environment or maybe Linux environment. She may have developed in a 64-bit on a 64-bit platform. This guy may be using the library in a 32-bit platform or maybe 16-bit embedded platform. Okay, and there'll be other variants like what kind of cache the developer has and what kind of cache the end user has. Some of the software bugs, which may be because of race conditions in, say, a multi-core software library could show up only with a specific kind of cache configuration. So it's very important that the software test suite is run in the development environment of the system integrator. Only after running the software test suite, he'll start using the software library which has been given to him by the library developer. So software tests become a handoff criteria. If some tests fail, he'll give back that library and he'll tell the developer that these tests are failing, and she'll need to fix those bugs and then again give the library to the system integrator. Now the problem is, with FPGA based hardware accelerators and with SOC FPGA kind of software hardware integration becoming possible, when a hardware IP developer passes on a design to system integrator, now see the change. It's no longer an SOC integrator, it's a software integrator, because the hardware IP is now getting directly used by software people. So if he passes on system Verilog UVM verification IP, it cannot be a handoff criteria, because this software integrator will have no way to run UVM, system Verilog based UVM IPs. Okay, so it's like he develops, for example, that XML parser, and he passes on the RTL of the XML parser to the system integrator. This guy puts it on the FPGA. Now he wants to make sure that his FPGA is working. The integration of software with FPGA is perfect. Okay, and depending on what kind of platform he's using, so here there are a lot of variants. The software could be in a particular, so software could be running on ARM platform, software could be using Linux, or could be using Windows, and then the FPGA could be SOC FPGAs also come in multiple flavors. There are hardware accelerators which sit on PCI. There are hardware accelerators which sit on the processor itself. So there are going to be a lot of variants. The system Verilog UVM VIP will be useless for this guy because he can't run it. Even if he gets a system Verilog license, he'll only be able to replicate the simulation this guy has run. He will not be able to run that system Verilog based simulation at the point of deployment. Okay, so that's why this comment, your system Verilog VIP is awesome, but how do I run these tests in my software environment? Like this guy was able to run because he was also using system Verilog, though at the chip integration level, but this is a completely different level. So that's where embedded UVM comes in. You are able to run it on embedded platforms. You are able to run it on SOC FPGAs. You are able to run it on Android. You are able to run it on Windows, on Linux. Okay, and then because it's written in a language wherein you can directly invoke system level stuff. For example, for accessing the FPGA, for accessing any peripheral or any design which has been mapped to the FPGA, you need to make some kernel calls in Linux. So embedded UVM is able to do it right away. I mean, from within the test bench, and it reproduces the same stimulus which the same test bench, if it is used with RTL, so it gives us stimulus. It produces a random test, random stimulus for the design simulation. The same stimulus will be applied to the FPGA, and in case some of the stimulus fails, that test case can be taken back to RTL, and the same stimulus you will be able to replicate back into the RTL test bench. And then this point that this guy is using, because he's a software guy, he's using all open source tools. He's comfortable with Java, he's comfortable with C++, he's comfortable with Linux. They're all open source. He doesn't pay anything to any proprietary license company. So Embedded UVM is open source as well. So one is the licensing part. The other part is when you work with open source, you have more flexibility. If you want to customize the test bench, for example, for another platform, you can do it yourself instead of talking to the people who created a proprietary tool. So that's where this kind of flexibility is the defining part of open source. Okay, so now a very brief introduction to Embedded UVM. It's a complete implementation of IEEE UVM standard. It gets natively compiled to the platform you're using. If you're using Linux, it creates ELF executable for you. If you're using Android, it creates an Android executable for you. Similarly, on Windows, it can create a Windows executable for you. It creates shared libraries which can be loaded or which can be binded using VPI or DPI with any Verilog or VHDL simulation. It is multi-core powered, thereby it gives you, it's the only multi-core powered UVM implementation in the world today that I know of. So you have implementation in System Verilog. System Verilog doesn't have multi-core constructs, so can't be. So the UVM is not multi-core. There is a UVM implementation in System C, which is again not multi-core enabled. This is the only multi-core enabled implementation of UVM. There are other nifty features like multi-UVM root. We can talk about it later. It's a somewhat advanced concept. It is ABI compatible with C++. So we talked about how System Verilog, when it integrates with C or C++, it has a DPI layer which becomes a runtime overhead. So in Embedded UVM, there is no layering when you want to talk to C or C++. It will directly call C++ or C functions. So there is no overhead. It has an LLVM based compiler, so which is again a slightly advanced concept. It's a software concept, but that basically means it can be made compatible with a lot of tools. Okay, so that's most about it. So these are various embedded platforms, including BeagleBone, Raspberry Pi, Intel Edison, Raspberry Pi, Panda board, or Droid. All these boards can run embedded UVM. So now for emulation, we had a presentation on emulation by Mentor Graphics. So that's a commercial and a very professional emulation platform. Here we are talking about small emulation platform, which is useful for learning and which may become useful as FPGAs involve and as SOC FPGAs evolve for IP level emulation. So this is what we do. For a commercial emulation platform, you have a test bench running on host processor. So this will be a generic server like an Intel or AMD server, and it's running System Verilog simulation. And then this is what will happen through PCI or some other. So some platforms, some emulation platforms are which are FPGA based. They are putting FPGA cards on the PCI bus. So that's how they communicate. There are other possibilities where you communicate via gigabit Ethernet interface between the emulation platform and the simulation that is running on your host processor. So this becomes a very extensive interface, and actually the emulation platform itself is very extensive because it's very big and very costly. So what we are going to learn and what we have with embedded UVM is it's as simple as this. We take SOC FPGA device, we put the design on the FPGA, and we put the test bench on the processor, which sits right on the same chip. And we have a very powerful and very, I would say, large throughput. This interface between the processor and FPGA on Cyclone 5 is 10 gigabit per second, that kind of interface. So it's a very low latency and high throughput interface. So the test bench is very quickly able to communicate with the FPGA, send the data to FPGA, and whatever the design response from that data, from that stimulus is, it takes it back to the test bench. So that makes a very simple, I mean, for a $130 Cyclone 5 kit, you get to run emulation on a small design that you put on the FPGA. So it's only $130 kind of investment for learning that you'll have to make. As the FPGAs evolve for bigger, when you have bigger FPGA cores, you will be able to do this kind of stuff for complex IP modules as well. Okay, so during this workshop, we are actually going to do this. We are going to put the design on the FPGA fabric. We are going to invoke the test bench from the processor, and we are going to run this little emulation. And we are going to see 100 times speed performance improvement over RTL simulation. Okay, so these are the boards that we could be working on. I'll actually be using the 10 nano, which is a very small board, almost credit card size. It has 800 megahertz ARM Cortex A9, also has Cyclone 5. Actually, this ARM processor is part of the Cyclone 5, and it costs only $130. There's a slightly bigger version of the kit I have, but this is more suitable for college lab environments, because it also has very nifty user interfaces in terms of LCD screen and the LED displays over here. For if you want to do something personally, this D10 Nano is a very smart kit. It only costs $130. So that's it. I'm open to any questions.
Good afternoon, sir. Sir, in the question answer section, there are a few questions for you.
Okay, let me. All right. Okay, so I see a tab which says My Q&A. So should I look at that, or I should look at the general question answer?
So the general question answer, sir.
Okay, so
for AI application, which is the must FPGA, sir?
Which question is that?
So the last one from
For AI
Prajwal, sir.
applications, which is a must FPGA. So
Puneet,
I'll
I think
rather let Ritesh answer it. Yeah.
Yeah, so that will be covered in tomorrow's session by Vikas. So we can take it tomorrow.
Okay, so there is the question, what's the use of DPI? DPI is system Verilog specific. It's the interface between System Verilog and C, C++. So for example, if you want to pass an array of data to C++ from System Verilog, then there is a set of functions you'll need to call in System Verilog, and on the other side to receive that data in C or C++, and thereby we'll be able to exchange data between the two. That layer is called DPI. The full form is Direct Programming Interface. Okay, so we don't need to use DPI because we are not using System Verilog. Okay, so now there's somebody asking for PPT. I don't have a PPT. I basically had a PDF file. I can share that PDF file on the WhatsApp groups. Then how is embedded UVM different from UVM? Actually, I won't say it's different because it's a complete implementation of UVM as an IEEE standard. IEEE standard is agnostic of System Verilog. So IEEE standard never says that UVM implementation has to be in System Verilog, and therefore it's not different than System UVM. It's UVM. So a better question could have been, how is embedded UVM different from System Verilog UVM? It's a complete implementation. So if you are learning embedded UVM, you are learning UVM. It's a line-by-line complete implementation. So you have the same methods, same classes, the same way to inherit from classes. So it's slightly different when you integrate your test bench with RTL simulation or with the FPGA for emulation. So that part we'll be covering during the workshop. Is it possible to write software programming after exporting the design hardware, sir? So the question is not clear. If the question means that once you port a design on FPGA, then is it possible to write software program which interfaces with the FPGA? Yes, that's part of the workshop that we'll be doing. Ritesh will be showing you how to do it for bare metal as well as in C++. I'll also be doing it for embedded UVM. And then is it based on embedded UVM based on SV? It's not based on SV, but it basically implements most of the constructs of SV. So we have constraint randomization, we have the whole UVM library, register verification, everything. Then there is a question which asks, where can we learn embedded UVM and which tools will support? We'll be learning embedded UVM during this workshop, and hopefully we can learn it later on as well if you intend to do a project using embedded UVM. How do we accommodate dynamic nature of test bench on emulator or FPGA which is static in nature? Okay, we don't port the test bench to the FPGA. The test bench runs on the ARM processor, which sits next to the FPGA. So embedded UVM doesn't do any kind of test bench synthesis. I didn't understand the point of running System Verilog on processor. What does it mean? We don't run System Verilog on processor. It cannot be run on embedded processor in the first place. We run embedded UVM, which is systems level programming. So it's kind of running C or C++ on the embedded processor, and we do it to create very small emulation platforms for learning as well as for what we call FPGA, SOC FPGA handoff of RTL designs. Can MCUs available in the market like ST32? Okay, actually, the questions, I can't scroll on this window somehow, so I'll take the next question. System C is really required. System C is required for virtual platforms. It is required because it runs much faster than RTL simulation, especially the TLM part of System C is very important. So System C, in a way, has started gaining some market hold these days because of requirement for very fast simulation. Is it fair to say embedded UVM is a step towards open source emulation? I would say yes, but then I have a biased opinion because I'm the creator of embedded UVM. Difference between Verilog and system Verilog. Verilog is actually there's no difference today because there's no IEEE Verilog committee today. Verilog has been merged into system Verilog. So system Verilog earlier used to mean kind of Verilog plus as C++ was to C. But today there is no Verilog, there is only system Verilog. There is no Verilog standard. After 2005, there is no new Verilog standard. Please let us know how FPGA is useful to data center. So basically, for example, I talked about that XML parser, which somebody implemented on FPGA, and it became 3,000 times faster than any C or C++ implementation. The same way when you are doing, so even XML parsing is data crunching. So if you want to do data crunching, wherein you can't use ASIC because it's very specific to your application, then FPGAs become very useful. System C is really required. I think I already answered that. For this coursework, can we survive without coding skills? You can survive, but if as I said, if you want to be in verification, you need to focus on programming. So if you want to learn programming, I'll be teaching object-oriented concepts and the basics of writing test bench. So this workshop is good for you. But if you don't have aptitude for coding, then you need to see whether you want to attend the workshop or not. If we load test bench on ARM processor on our board, how will we emulate SOCs here, since it will need firmware to be loaded on the ARM processor? Okay, we'll talk about the firmware part. We'll actually Ritesh is also going to talk about that. We'll see how we create small calls to the kernel to access to make access on AXI bus, as well as we'll learn about device trees, which enable us to talk to FPGAs from the ARM processor. As PSS is coming, UVM is useful. PSS is it's not coming. It has already come. Still, I would say random stimulus generation will not be substituted. It may be complemented by PSS, but it will not be substituted. And as hardware and software co-verification become mainstream, random simulation will also gain a lot of space in future. For UVM, Verilog or VHDL is effective. UVM is closer to Verilog than VHDL. Though even if you have designs in VHDL, you can do UVM-based test benches, but it's closer to Verilog. So it's effective for both, but closer to Verilog. Veloce Fault app is open source. I don't know about that. Please repeat the static and dynamic part you discussed while discussing embedded UVM. So static part and dynamic part, I'm not very clear whether it's with respect to multi-core processors, where I talked about RTL simulation can be multi-core enabled in a different way, but behavioral simulation needs different type of constructs. We will talk about it on WhatsApp group if you want a detailed answer. Why is that hardware speeds up a process compared to software? Because hardware is highly concurrent. Hardware doesn't typically interface with memories, and memories, any access to memory is slow. Okay, hardware may need memory, but for example, in software, you will have all the instructions on the memory, and memory access will make and then software is sequential in nature, hardware is concurrent in nature, and that's why you can have multiple multipliers running in parallel or in your DSP, for example, and stuff like that, which will be very fast. And software again is running on a general purpose, on a very smart but general purpose, I would say, arithmetic processor. But for hardware, you can make application specific arithmetic operations which are going to be faster. So typically, that's the kind of speed gain you are going to see. 3000 as that XML parser tweet said. At the end of the workshop, will there be any project for better learning? Yes, but it depends on what you want to do. You can get involved in RISC-V verification if you want to. You can get involved in open source verification projects as university projects. I'll highly recommend that, because when you take a project to the next level, to an interview or for your placement as a university lecturer, or even for writing a white paper or publishing a paper, you can refer to GitHub, and you can basically make better references to your project in your presentations. So people who, it's like, if it's a closed source project, then you may be bluffing, and 90% of the closed source projects bluff at some level. But if it's an open source project, you can't bluff, and that's the confidence in the audience also. Okay. So again, that's a question on static and dynamic part. I also already answered it for multi-core perspective. There's a question which Ritesh already answered. So better place to learn OOPS concept used in. Okay, so for 2 days in the workshop, we'll be learning OOPS concepts, and these OOPS concepts are going to be same as OOPS concept in System Verilog. So don't worry, we'll cover that. Are we going touch scripting related topics? That's not. It doesn't make sense to me. The question you need to ask that in a different language. I see embedded UVM supporting multi-core, which is definitely much better than UVM, which does not support. Why industry is still using System Verilog? So hardware industry, people are looking for alternatives even to Verilog. There is a MyHDL project, which is a Python based alternative to Verilog, but the way the hardware industry is, it's not today. It's not supportive of open source, but I see that changing with RISC-V and with FPGAs becoming mainstream. So hopefully there'll be better adoption in future of open source projects. How much time it will take to complete simulation of an FPGA for a typical system? Okay, simulation of an FPGA in a typical system depends on your design. If it's a design that requires very extensive simulation, it may even take weeks. Okay, just for reference point, when we talk about present day processors done by the processor companies, the simulations run for those processor cores, the verification of those processor cores for 6 months on 10,000 machines. That's the kind of data, okay, for fully verifying a processor core. So it really depends on what exactly you want to do. So on an FPGA, you can as well fit a very extensive RISC-V core that will take a lot of time to verify. Can we do STA on SOC FPGAs using embedded UVM? No, but when you map a design to FPGA using Altera or Intel tools, then part of the synthesis and place and route process is also STA. So STA will automatically happen there. YAML language required? No. YAML, by the way, stands for yet another markup language. It's a very generic language for data exchange on the web servers, etc. So I don't see any relevance of that language here. I don't have a laptop with me. You are good to go. Attend the workshop. We'll be running all the labs as we go. The instructor will be running the labs, and we will be leaving the instructions on GitHub, or we'll be sharing the instructions with you, and you can replicate the labs whenever you go back to your college. When will be software downloaded will be discussed and used. Tomorrow we have quarters, so I encourage you to focus on quarters. Make sure you have downloads for quarters so that you can go through the labs tomorrow. A day after, we'll talk about embedded UVM. Hands-on session, what can I do? You will be doing it along with whatever the instructor asks you to. So there'll be labs on GitHub. I encourage you all people to create an account on GitHub so that you can have a more fruitful lab session. You can modify the labs and keep for yourself, that kind of stuff. Political required for this course, not for embedded UVM, for quarters. If you learn Tickle, it will help you automate. But for tomorrow's labs, I don't think it's required, but it's good to learn in future. Why we need those languages for VLSI? So these are languages for modeling as far as design is concerned. And as I told you, there's a very thin line separating hardware and software now. Hardware will integrate with software in a very tightly bound fashion. That's one thing. So it's good to know languages from that perspective. Secondly, in hardware designs, we are trying to do more or less what used to be done in software 5 years earlier. So actually those languages will have to become more and more sophisticated in future. So it's not about why we need those, it's about we need those much more now. Can you actually there are a lot of people working towards making C and C++ synthesizable, though only a very small part of C++ or C can be synthesized today. So that's the state of the things today. Can you later after this workshop also guide us in some advanced projects on functional verification using UVM? Surely, I'll be happy to do that. I downloaded and tried to install, unable to install properly. So you need to specify, we can discuss it on WhatsApp. So let us know the error, send a screenshot. There'll be other people as well who have installed, so they'll be able to help, and we'll try to help as much as we can. Ritesh, you can also interact because Ritesh is a Quartus expert. So you can interact with him. I see embedded UVM supporting multi-core, which is definitely, so I already answered that. Can you later after this workshop, I already answered. Recorded sessions, you need to talk to Firoz. I think they'll be made available because tomorrow onwards, we are going to have sessions on YouTube, and probably that means that recorded sessions will also become possible. Embedded UVM, UVM, SV UVM are different in implementation, but we subscribe to the same IEEE standards. So the concepts are same, and the way we create test benches, it's all same. The implementation is different, but its implementation is also line by line. It's a port of SVUVM, so you don't miss anything. How is FPGA bit file different from RTL? FPGA bit file is the synthesis result, synthesis as well as placement and after placement and routing, whatever that result is. It's also, but FPGA bit file could represent various things in future for partial reconfiguration of FPGAs. It could even mean just the synthesized plus meta information of RTL synthesis result, which will be dynamically placed at the time of mapping to to the FPGA. So we will talk about it later during the workshop, so you'll understand it better.
अच्छा सर joined है.
Okay, then there is, do we have any session on how to follow and get used to GitHub usage? Just do it, it's not tough. So GitHub itself is having a tutorial on how to use it. We'll be using it, so we'll use it and learn it. That's the only way to learn when it comes to programming and it comes to hardware. So you can't learn, for example, cooking by reading a recipe book. You learn cooking by cooking. So we'll use GitHub and therefore we'll learn. Sir, after installation, Quartus Prime Lite, the open, but it's showing buy software. So it's showing, it's probably giving you an option to buy the software. That's what I know. So you don't have to buy because we'll be using the free parts of Quartus for this workshop, and they are sufficient for learning. Embedded UVM, okay. Ritesh sir, please share your email ID. You can ask your questions on WhatsApp group. If we can't solve it, I'll be able to interact with Ritesh and I'll be able to get his help. YouTube channel, there are certain people asking about YouTube channel. Firoza will share the YouTube channel with you tomorrow. So that's where you will, she's going to share the link. How to develop a VIP, we'll be covering that during the workshop. As embedded UVM is different from SVUVM, which language is used for UVM. We use an evolution of C++ called D language. Now D language has garbage collector. It has a lot of similarity with system Verilog, and that's why the end result you will find is going to be similar to system Verilog. Plus D language has a very good support for multi-core, and while coding embedded UVM, we made sure that embedded UVM is multi-core compatible, and that's how. So there, at the back, we got a lot of support from D language to make things happen. How to contribute to open source projects in VLSI design on verification. So it will be covered during the workshop. Actually, it's just about taking one example, learning from it, modifying it, create your own examples. The major part of it is not to feel shy. If you are learning, you are learning. There's no point feeling shy of doing things. Okay, so there's a special thanks for mentors. I don't know, that's to the instructors or to Mentor Graphics specifically. Yeah, but you are welcome. Anything else? Firoza, if you have anything, if you think I need to answer a question, please let me know. Okay,
Yes,
I'll be available. I'll also be available on WhatsApp, so you can ask questions there. But for now, I think we need to focus on Quartus, and we need to make sure that everybody who wants to go through. Actually, we all want to go through the labs tomorrow. So please install Quartus. Please do it today. Don't leave the things for the last hour. Do it today because it's a big download and you might face problems installing it. Ritesh already shared his email ID in the question answer session. So if anybody has some issue with installation, please drop an email to Ritesh. But it's much better to talk to drop your question on WhatsApp first, because you get a community support on WhatsApp. So only for problems that because I don't want to crowd Ritesh with all the questions. So only if some question gets unanswered and some issue remains unresolved, we can drop an email to Ritesh.
Sure. So please, yeah, so you can drop your queries on WhatsApp, and then if required, you can share it on. Yeah, as Puneet said, we can write an email.
Thank you, Puneet sir. So, yeah, thank you, Ritesh sir. So, there are a few announcements for the participant. First of all, the YouTube channel is already live. The streaming from today 12 noon we already started, but the YouTube channel is not for the registered participant. I request you to please note that there will be a system generated attendance which will be generated at the end of the session, and that attendance report will be used for identifying the participant who will be getting the certificates, because 75% attendance is a mandatory, and based on that only the certificates will be issued. So I request all the registered participants to please join us through the invite that we will be sending you. YouTube channel, you can refer to the participant who are not registered but they want to attend the session. For them, you can refer to your friends, to your colleagues, so that they can visit the channel. The channel name is E&ICT, E-ICT Academy IIT Guwahati. So you can just search in the YouTube channel. The link, today's session will be available there. So this was the first announcement. Second announcement is that tomorrow we will be having one MCQ from 2:30 to 2:45. So I request you all to be available. The session will be over by 2:15. After that, there will be a 15 minutes break, and then from 2:30 we will start the MCQ question. And the third announcement is that all the participants will get the link for the course material which is uploaded in a drive. So all the links will be given to your WhatsApp group or through email. So I request you to please be active over email, the registered email, as well as in the WhatsApp group that you have joined. So these are the three important announcements. And regarding the all other, regarding the certificate and the regarding the attendance, I request you to please drop me question answer in my panelist option, and all the question related to the technical session, I request you to please drop to all. Thank you. So Puneet sir, can we conclude the session for today?
Yes, Firoza, thanks a lot for the support, and hoping to see everybody tomorrow morning. What time does the session start tomorrow?
So 10 a.m. we will be starting, sir.
Okay, so please, everybody, please come in time so that we can start on time.
So thank you, Puneet sir. Thank you, Ritesh sir. Thank you, Vikas sir. It was a wonderful experience, and all the participants enjoyed a lot. We are getting good, like the feedback we are getting continuously in the WhatsApp group. So thank you, sir, for the session. And I will request all the participants, please join us by 9:45 tomorrow so that we can start the session sharp at 10 a.m. Thank you.
Thanks, Firoza and team. Thank you, Puneet. Thanks everyone for joining this.
Thanks, Ritesh.
See you tomorrow.
Thank you.
Good night,
Thank you, sir.
everybody. Good night. Bye.
Good night.